as well. Okay. And Shailja, how scientists find that which place earthquake will come? So it is not as if they are able to predict that, okay, at this particular location, at this particular latitude and longitude, there will be an occurrence of an earthquake, but they are able to at least identify the regions where this earthquake is probable to happen. And how is that? Is by studying the rocks. So by studying the rocks, they get an idea about the amount of deformity that the rocks are undergoing. They know the stress handling capacity of the rocks, and they know that beyond a particular limit, as the rocks will deform, either they will try to get back into their shape, or there will be a crack or the breakage. In either of the case, there will be an earthquake. And also there is a concept which is referred to as, so this is just for your information, not very much required for your general studies. Just listen to this particular concept, and that concept is about seismic gaps. So what do we understand by seismic gaps is basically, see, let's suppose you consider the entirety of the portion of Himalayas. I'll show you with the help of the image as well. So let's consider the entirety of the portion of the Himalayas. Now we do know that there is significant amount of deformity right from the northwestern part to the northeastern part. The rocks will try to get into their original position, leading to earthquakes. But then upon looking at the past data, geologists, let's suppose they come upon a finding that in this particular region, even if there is a high probability of occurrence of earthquake, there has not been a massive earthquake which has occurred in the past 200 or 300 years. Means for the past 200 or 300 years, there has been deformation, but no earthquake has occurred. So that means this region is due for a massive earthquake. And that area which is experiencing a lack of seismicity as of now, that means in future there's a probability of very high magnitude earthquake, leading to the rocks coming back to their original position. That is referred to as a seismic gap. So for example, from Dehradun in Uttarakhand all the way till Kathmandu in Nepal, there does exist a seismic gap. Now, that is why, and scientists have known this, geologists have known this. That is why 2015, you had a massive earthquake in Kathmandu, which relieved some of the pressure. But it is expected that one such massive earthquake will come on the Uttarakhand side also in order to relieve that pressure. But the timing of it, the exact when of it, that is still very subjective. Okay, I hope that is clear. And seismicity, Shruti, is basically anything associated with earthquake movements. And yes, yes, Chavan, you should start answer writing immediately after that. Induced seismicity, Ujjwal, basically in the case of the dams, whenever you have the presence of a dam. Now, dams include many of them a large storage structure and a large concrete construction as well. So all that water which is stored along with the huge amount of concrete, that puts enough pressure to create various cracks upon which the rocks can end up sliding, creating an earthquake. Or also you can have the rocks getting deformed under the pressure. They will try to reform and gain their original shape, and that is where also you will have earthquakes. Sneha, the question is, plate tectonic theory is the resultant of the theories of continental drift, convection current, and seafloor spreading. Yes. So as we have already discussed, Sneha, that all the earlier theories that we have gone through, all those theories have contributed to some extent, and that has led us to understanding of the plate tectonics. For example, continental drift, that provided us evidences that the continents can move, isn't it? So that evidence of the movement of the continents indicated, now that helped us to formulate the plate tectonic about the movement of the plates. Then seafloor spreading helped us understand about the creation of a newer crust. That is something that we experience in the case of divergent plate. Convection current theory, that helped us explain about the transfer of heat from the interior to the surface, and that leads to the crustal movement overall. So how all of these lead to one or the other factor of plate tectonics. And then basically in this answer, what you have to do is you have to take out the concrete derivations or concrete conclusions from each of the theory, and then You have to link it to the details of the continental drift, that how this portion has been extracted from convection current, this portion has been extracted from seafloor spreading, and this portion has been extracted from the portion of continental drift. Okay. For your prelims, generally, Asha, the questions are asked from the plate tectonics theory. Rift Valley, Satyapal, is basically the kind of valley structure which is created due to tension. We will take a look into the formation of Rift Valley today. Okay. Plate tectonic theory, Sayyid, was given by many of them, and you had Morgan, Parker, Wilson, all of them, Mackenzie, they were involved. Now, all of them, they submitted their papers individually. So it is not a brainchild of one individual, as you see in the case of seafloor spreading or continental drift or convection current. So that is why all of them have actually contributed. Okay, and Mayank, will we be seeing the topics like different cavities? So last time also I had asked you which cavity are you talking about, and there is no such large gap in the region of the mantle because it is filled. There is expected to be a certain gap between the outer and the inner core, but not in the region of the crust and the mantle. Okay. After that is good. How do scientists predict eruptions, volcanic eruptions? Again, by looking at the underground region. Okay. Big Bang Theory, the basics of it, you should be able to know, Praveen. That is relevant for your prelims. And that is something, again, you will be required to study in detail in science and tech. Is era or epochs important to learn? No, not so much. Just gain an idea about which era is referred to as the Hercynian age, Cambrian age, etc., and Ordovician age. That will be more than sufficient. And difference between love and Rayleigh wave is the simple difference on how the ground ends up moving. In the love wave, the ground indicates a kind of a horizontal movement. In a Rayleigh wave, they indicate a kind of a wave-like pattern. Can a volcanic eruption be stopped? No. Okay. Mercantile scale. What is mercantile scale, Shiva? Are you talking about Mercalli scale? Mercalli scale is basically the scale which is used to identify or classify uh, the earthquake based upon the type of destruction which has occurred, amount of destruction which has occurred, whether the buildings have remained intact, whether the trees have actually shaken during an earthquake. That is your Mercalli scale. Kant, Laplace theories and nebular hypothesis not required for the exam. It is not being asked in the exam for the past decade and a half. That is why we have not discussed that. Okay. Discontinuity we have already covered, Mayank. Please look into the annotations of the previous PPT. Big Bang theory is the only theory out of all the various Kant, Laplace, Chamberlain, Jeffreys, all the theory that you come across. Big Bang theory is the only one relevant for your exam. And seafloor spreading. Seafloor spreading, first of all, understand that that theory had limitations and it was rejected. And how is it the mid-oceanic ridges? Basically, there is divergence. Because of the convection current, there is creation of a newer crust by volcanic eruption at the region of mid-oceanic ridges. And as the newer crust gets created, now the convection current will have a horizontal arm as well that will pull apart the land, and that is where newer crust will be created in the gaps in between. Yes, Gulam, you can do that. Okay. We'll come to that, Kavya, when we talk about the climatology. Ashay, I already told you that for your prelims, the plate tectonic theory is more important. Okay. Is it must to learn the rainfall, millimeter, and all numerous information of any area or river? Absolutely not, my dear friend. Absolutely not. Netra, body waves are the ones which travel through the interior of the body of the planet. Surface waves are the ones which are generated on the surface once the body waves hit the surface. And Ainum, your question is now visible, but then I can't see the question. Patel, Twisha, should I mug up all in the book or PDF. The PPT, the annotations of the PPT, along with additional reading material, again, I will repeat, along with current affairs, is more than sufficient. Yes, Akshita, that is correct. Shadow zone, basically, Ravi, they indicate those wherever an earthquake occurs. From that, the seismic waves, the body waves will be emitted, but due to the bending of the body waves, there will be certain areas which will not be able to detect those body waves. Those are referred to as the shadow zones. Travel through the outer core. Kindly look at the recordings of the videos which are available. We have initiated the discussion for volcanoes in the previous session. We had started looking into the fact that what is a volcano. We had looked at the schematic diagram of a volcano as well. We had looked at the fact that when you have molten materials present in the interior of the planet, now those molten materials, which are actually about to come out, now those molten materials, they are referred to as magma. The moment they erupt onto the surface, that is what we refer to as lava. So today we are going to carry out the discussion further from here. We are going to study more about volcanic eruptions. Where is it that the volcanic eruptions happen? And even though we have studied that in the portion of plate tectonics as well, when we were talking about the various different types of plates, we have studied about volcanic eruptions and in which conditions the volcanic eruptions they do occur. So we are going to further develop on that concept, and we are going to look into what is a caldera, what is a mantle plume, what do we understand by when we talk about the volcanic hotspot, what are the physiochemical properties of the lava, the magma that we have, which ends up determining the types of rocks also getting created. And then we will come to the final portion of endogenic forces, which ends up creating various different types of folds, ends up creating different types of fault lines. That is something we shall be concentrating upon. Okay. And so we continue with the session, and watching your classes in recorded form and making notes. Should I read NCRTs? So, not very much required. If you are very religious with the class along with the additional reading material, not very much required. Now, okay, few of you had sent me a mail regarding, so I have sent all of you the various different mails that you had sent. Few of you are still remaining. Now, a couple of you had sent me a mail about international dateline and the understanding about international dateline and time zone. I would rather now direct you to our YouTube channel where the animated video is available. So kindly go to the YouTube channel and the Byju's IAS YouTube channel and take a look at the animations of the IDL so that you get a clearer idea about IDL in detail. Okay. Now, let us continue with the portion of volcanoes now. So here, link please. That much you can find out, my dear friends. If I provide you with the link here itself, that much at least you can search on YouTube. I'm sure you will be searching many things on the internet. This much search expertise I am sure you will have on YouTube, so rather than having the requirement of the link. So yeah. So when we talk about the volcanic eruption here, let's suppose, how is it that it happens? Basically, talking about the schematics of it. So here you have the presence of molten materials. Now, molten materials, when they are present in large chunk, now there you will also have the presence of gases. Now, this portion, that is what is referred to as a magma chamber. Now, immediately the question which should erupt in your mind is, or emerge in your mind is, that where is it that this magma chamber is situated? Is it located in the crust? Is it located in the mantle? Where is it situated? Is the magma coming all the way from the region of the outer core? So here, magma chamber is mostly located in the region around Moho. What is Moho? Let me see if we are aware of that or if we recall that. When we say Moho, which area are we referring to? Very good. The discontinuity between the crust and the mantle. Good. So basically, majority of the magma chamber that you will find will be in the vicinity of Moho discontinuity, either slightly below it at the Moho discontinuity or in the region of asthenosphere, some distance away from Moho. That is where all the molten materials they start to accumulate. Now, when the materials will melt, there will be the formation of various different gases as well. So, in this magma chamber, you will have the presence of molten materials plus gases. Now, which are these gases? We have already discussed in the last class which gases are constituted here. So, the gases which are formed are generally water vapor, which is the most predominant gas which is created. So, you have water vapor, then you have sulfur dioxide, carbon dioxide, right? Carbon monoxide. So these are hydrogen. These are few of the gases which are released, and water vapor is the most predominant, the most dominant gas which basically is emitted. Okay. Now, here the portion basically from where and the channel or the pipe like portion from where the molten materials will try to escape or they do come out, that is also what is referred to as the volcanic vent. Volcanic vent. Now here what do you observe is that all these molten materials, they keep on getting heated up, and thereby the gases, they provide them with the pressure. Now, the pressure provided by gases is very, very important to pull the molten materials up. Otherwise, also, molten materials, when they are in a liquid state, liquid is lighter than the solid and it is hot as well. It will try to rise up. But if the crustal portion, if the portion of the upper mantle, etc., if that is very hard, then the molten materials won't be able to come through. It is the pressure provided by the gases which helps them break through the surface. Now, in cases where, let's suppose, the gases are not present, you only have the presence of molten materials. Many of the times, you will observe that the materials, they try to come to the surface, but they are unable to break through the surface, because to break through these rocks, you require huge amount of pressure. So that is where the molten materials, rather than coming out, they will start solidifying here itself. They will spread out here in certain sections, and they will solidify in larger chunks, for example, like this, and so on. So it ends up forming intrusive rock formations, the intrusive igneous rock formations that will be created in the process. Okay. So that is where the presence of gases is a must. It is these gases which allows the materials to come up, spread on the surface. It can end up forming a conical mountain by the accumulated materials. And once it comes on the surface, those molten materials on the surface, they are referred to as lava. Okay. Then they solidify to form the extrusive igneous rocks in general. Now, all these volcanoes, all the various different volcanoes across the planet, you have evidences of volcanic eruptions going back millennia, right? Going back hundreds of thousands of years. Now, all the volcanic eruptions, they don't happen at the same frequency. In certain cases, the volcanic eruptions keep on happening almost every 10 years, 20 years, 30 years, 50 years, 100 years, or so on. In certain cases, that eruption is something which has not happened for 400 years, 300 years, but there's a probability of that erupting again in the near future. In certain cases, there has been an eruption which has happened long, long time back, maybe 100,000 years back, and there is no expectation of any further eruption happening there ever again. So, accordingly, based upon the frequency of eruption, the volcanoes are classified into active, dormant, and extinct. Okay, based upon the frequency at which the volcano is erupting, it is classified into active, dormant, and extinct. What is the meaning of it? Active. Active means it is still experiencing significant amount of volcanicity. Means at any point of time it can end up erupting again. Then when we say dormant, dormant means it indicates something which is resting, which is not very active, right? Dormant is used in that parlance in the English communication skill, that you have something which has attained dormancy, means it is not very active anymore. So dormant volcanoes are those where the eruption has happened some time back, long time back, but there is a probability that in future an eruption can happen again. We don't know when, but then eruption can happen again, maybe 20 years from now, maybe 200 years from now, maybe 30 years from now, but eruption can happen again. That is dormant. And then you have the extinct category, where earlier volcanic eruptions used to happen, but now there is no scope of volcanic eruption happening there ever again. That is extinct. So that is the classification. So this is based upon the frequency of eruption. Now, as you can see in the image, when we talk about the active volcanic eruption, now there the magma chamber will always represent a kind of a filled up format, where the magma chamber is also filled up. There are presence of large amount of gases as well. So there is always a chance of fresh eruption. So example, you can take many of the examples for active. You have Mount Pinatubo, one of the most violent explosions in the last couple of 3 decades. Where is Mount Pinatubo situated? Let me see if we have an idea. Where is it that we have the location of Mount Pinatubo? Very good, Manikandan. It is in Philippines. Okay, that is in Philippines. Now in India, you have only one active volcano, and that is Barren Islands. That is situated in Andaman Nicobar. Okay, Barren Islands is the only active volcano that you have in India, that is situated in the northernmost extent of Andaman Nicobar Islands. And in fact, it represents a larger convergence of ocean, which has ended up creating not only the Andaman Nicobar group of islands, but further south, it has also been responsible for volcanic eruptions that you see in the region of Indonesia, and also the creation of many islands in the Indonesian region. Last time the Barren Islands volcano experienced an eruption, it was in 2017. That is where some amount of molten materials along with a lot of gases, they were ejected from the Barren Islands. Now UPSC asked this question in 2018 prelims, where in one of the statements UPSC framed the statement as the last time the Barren Islands erupted was in 1991 and has not erupted ever since, which again tells you that anything relevant with the portion of current affairs, you can expect a question of static portion associated with that current affairs. Okay, so any portion of current affairs regarding, let's say, earthquake, volcano, climatic conditions, when they are in discussion, you can always expect a static question based upon the general concept being asked in the examination. Okay, so these are, then you have many of them. You have Stromboli, Etna, Vesuvius, many of them you can count as an example of active volcano. Okay, now then you have, and you can locate the Barren Islands in the map in Andaman Nicobar. It is in the northern portion. Then you have dormant volcano. Dormant means the eruption has happened in the past, and there is expectation of further eruption happening in the near time future, right? That is what is referred to as dormant. Example, when we talk about the example, okay, good. Kilimanjaro is one of them. Mount Kilimanjaro basically has got three different volcanic peaks in that region. Out of those, one peak is considered to be extinct in the sense that there is no further volcanic activity which is expected out of that region. But one of them is where the volcanic activity is something which is expected in the future. Okay. How many of us we don't understand the English meaning of dormant? Dormant means something which is not very active. That is dormant. Okay. Now, then you have Mount Vesuvius. So, Mount Vesuvius, basically, you have a very famous anecdotal story associated with it, that Mount Vesuvius earlier was thought to be extinct, that there won't be a volcanic activity happening there ever. But then, around 78 AD, you had a massive eruption happening there, and the entire city of Pompeii, which was situated on the slopes and in that nearby stretches, everything was completely destroyed. So that was a surprise for everyone around 78 AD. But then thereafter, again, there was an understanding that, okay, the eruption can happen. It did not happen for 100 years. There was always an expectation that eruption can happen. It did not happen for 500 years in the case of Vesuvius. It did not happen for 1,000 years. So people thought that Vesuvius will never erupt again. But again, in the 1500s, Vesuvius exhibited another eruption, consuming again another settlement which had happened to occur around its sloping region. So that is where the dormant ones, they can erupt after maybe 500 years, maybe 700 years, maybe 1,000 years. They can always indicate a kind of an eruption. Similarly, you have Krakatau. Where is Krakatau situated? The Krakatau eruption. Very good. Where is it situated? This is Vesuvius. This is Krakatau. Very good. It is in Indonesia. So the Krakatau eruption is considered to be one of the most massive in the past few centuries, in the past 2 to 3 centuries, because so it is situated in the western part of Indonesia. So that is where, when the eruption happened in the 1880s, it was basically one of the most massive eruption, where it is said that the explosion is something which could be felt as far as Turkey and Japan. So understand where is Indonesia, understand where is Turkey, and where is Japan. So, and in that region, so much amount of dust and cloud smoke was created that sunlight was blocked for a few weeks. The amount of carbon dioxide emitted during the Krakatau eruption, it is said that it would take almost 200 years for all that carbon dioxide to be dissipated in the atmosphere. So that was very, very massive. Okay. Then we have the extinct volcano, where the volcanic eruption has happened earlier, long time back, but now there is no magma, there is no molten material in the magma chamber. So there is no expectation of further volcanic eruption happening. So in this, no expectation of further volcanic eruption. No further volcanic eruption expected. Example, no, Mount Fuji is not extinct. At max, you can classify Mount Fuji into slight amount of dormancy, but it is not extinct. Yes, very good. You have the example of Mount Kenya. Dhosi is again, Dhosi Hills is where you have also the evidences of caldera, but long time back you had the eruption there as well. Okay. Yes, Mount Thielsen. That is in United States. Okay. When the lava comes out, does it produce harmful gases? It does emit in the eruption process. It does release a lot of harmful gases. Okay. Right. Pacific Ring of Fire will have many examples of active and also in certain areas dormant volcanoes. Caldera will come to it. So These are basically the types or the classification based upon the frequency of eruption, that how frequently the eruptions happen or how regularly the eruptions end up happening. Now, here, if you have a query that when is it that we consider it as an active one, when is it that we consider it as a dormant one? So if the eruption, let's say, has been happening very frequently, has been happening every 100 years, there is an eruption, every 50 to 100 years, there is an eruption, or 30, 20 years, there's an eruption, you consider it as an active one. If there are large gaps in between eruptions, 200, 300 years of gap between the eruptions, you can consider it as a dormant one. If there has been no eruption happening for the past 500 years or more, 600 years, 700 years or more, 1000 years or more, that is when you consider it as dormant. And this is also understood by analyzing the portion of the magma chamber, where the magma chamber, the amount of molten materials that it has, the amount of gases that it has, that is a key determining factor of whether the eruption will happen again or not. So if the magma chamber is completely solidified, there won't be a future eruption happening in any time near future. So that will be extinct. Now, how do we get to know whether the magma chamber consists of molten materials, gases, or whether the magma chamber consists of only the solidified portion? How is it that we get to know? Apply your logic. Very good, Yuvraj. Let me see if anyone else can get it. How do we get to know whether you have molten materials in the magma chamber, gases in the magma chamber, or it is solidified? Vishnu, correct. Adnan and Purna, very good. Likhani, correct. Zeenat, Mahender, and Prem, correct. So it is by studying the seismic waves. And Afsha, correct. It is by studying the seismic waves that are generated. The seismic waves, they will travel throughout the planet. Even if it is an earthquake occurring somewhere in Alaska, the seismic waves will travel through the planet. And it is by measuring of those seismic waves where we analyze where is it that the solid portions have been encountered, where is it that liquid portions have been encountered, and where is it that the gaseous portions have been encountered. So that is how we come to a conclusion, okay, by studying the seismic waves. Now, then we come over to the schematic representation. So schematic representation of a volcano overall, it, you have to understand that it is not as if there is a mountain. Many of the candidates, they have that kind of a misconception, because, and I don't blame them, because right from the childhood days, whenever anybody sees a kind of a volcanic eruption, or whenever anybody is shown an image of a volcanic eruption, it is like a mountain or a hill on that eruption is happening. So many of the candidates have a preconceived notion that volcanoes will erupt only in the case of a mountain, but that is not so. Volcanoes, in fact, they rarely erupt amongst the region of the mountains. It is that the eruptions will end up creating mountainous format. How? So once the molten materials are thrown up with a significant amount of pressure, and the pressure is huge. Okay, many of the times at the time when the eruption is happening, when the molten materials, they are trying to come up, 2 to 3 days prior to the main eruption, in many of the cases, the region starts shaking, the region starts experiencing minor earthquakes, series of minor earthquakes. So whenever there are such series of minor earthquakes happening around the region of Pacific, particularly in the region around, let's say, New Zealand, Tonga, in southwestern Pacific, in the region of Indonesia, in the region of Mediterranean, where you have the Stromboli, Etna, Vesuvius, the entire chain which is there. Now, in all those, you will find that the surface that starts to shake. Now, which tells us that there is huge amount of pressure that the gases and the molten materials, they are creating to break the surface. Eventually, they will break through the surface. And that is when the molten materials, they are thrown up into the air. Now, when they are thrown up into the air, they will fall down immediately in the vicinity. They keep on accumulating. And that is how you have the conical shape which is attained. So volcanic eruptions, they end up creating a conical shape eventually by accumulation of materials. Now, the passage through which the molten materials eventually pass through. That is what is referred to as the vent of a volcano. Now, once an eruption occurs, let's assume, after that, things will cool down unless and until it is a continuous active volcano. Things will begin to cool down. Now, as things begin to cool down, all this will lead to formation of what? Solidified igneous rock, which is very hard. Now, the next time the magma actually wants to come up, and from the magma chamber, molten materials they try to come up, you have to understand that the molten material have to break through that entire solidified portion, right? Because in this entire volcanic vent, after the eruption, let's suppose in 2 years, 3 years, 5 years, 10 years, everything has solidified. Now, after that, when the molten materials they try to push through, they will have to break through all of this. Now, that requires tremendous amount of force, and that requires an explosive amount of eruption. So, in those cases, there's an explosion when the eruption occurs. And all these solidified materials, they are broken into fragments as they are thrown up into the sky. That is why, if you look at the videos of a uh, volcanic eruption which has erupted after a long period of time, you'll find that the smoke is absolutely black, and there is significant amount of dark materials, dark chunks of solids which are thrown up into the air and then which are distributed and they are thrown up larger distances. It is a solidified portion. Now, once that solidified portion is removed, then the molten materials they start coming out endlessly. So that is the process of eruption. Now, many of the times it also happens that the material has gotten solidified so significantly that fresh eruptions can't happen in that area, because removing all that solidified portion is simply impossible. So that is where you will observe that the molten materials they spread themselves in between the layer of the rocks, they spread themselves in between the various formations, and they solidify there itself. Okay, now let us take a look at the reason behind the eruption of the volcano. Now, when we talk about the reason for the eruptions, broadly, you can think about one reason. What is the major reason? It is the residual heat that is driving everything. But then, to come to the precise reason and the precision of it, it is initiated why? It is initiated due to the presence or due to the various different continental movements or the plate movements that you observe. Now, in the case of plate movements, which of the plate movements can initiate a volcanic eruption? So, whenever you have, let's say, plate movements, let's suppose. Now, these plate movements, in the case of convergence, wherever you have oceanic convergence, whether it is an oceanic or oceanic continental, wherever you have an oceanic convergence, there will be a volcanic eruption which will occur. Okay. Then in the case of divergent plates, whenever you have divergence of plates, there also you will have volcanic eruptions which will be very frequent, because as the plates they tend to move apart, there will be creation of a newer crust in between. So divergence of plates will also end up creating a kind of a volcanic eruption. And then you also have transform. Very rare occurrence. Now, why is it that in the region of transform faults or transform cracks, so as to say, why is it that their eruption occurs? Largely, volcanic eruption will be concentrated in this area. You also have a couple of other places which we refer to as volcanic hotspots, which we'll cover later. So when you talk about the reasons and the regions where you have the volcanic eruption, you also will have to include the hotspots, but that is something we'll cover slightly later. So here, when we talk about the transform type of plates, transform plates is when they start moving parallel to each other. And when the plates they start moving parallel to each other, cracks develop. Now it is due to the development of these cracks sometimes where the eruption can happen. How? Let us understand that. So before that, the volcano eruption begins with the formation of magma in the lower section of the earth's crust around the region of Moho, right? Around Moho and asthenosphere. Then, with pressure, magma travels upwards with tremendous force, hitting solid rocks and other material, and creates a new passage to the Earth's surface. Once it reaches the air, it is referred to as lava. Now, here, how is it that sometimes, in very rare cases, the occurrence of large and deep cracks, how do they initiate a volcanic eruption? So, for that, you have to understand what is Moho. Moho is the Morovicic discontinuity that we have covered in the earlier session. So, kindly refer to that. So, here, that is the place between the mantle and the crust, that discontinuity. Plug, volcanic plug that you see here, in this case, that is the solidified rock that you have in the case of the vent. That is what is referred to as a plug. What is a plug? When you fill a hole, that is what you, I have plugged the hole, isn't it? That is how it is used. So that is basically when you have the rock solidifying in that region. So here, when we have the eruption of volcanoes due to development of cracks, that is a very rare case though. Now, how does it happen? Let us understand that. Now, let us suppose I have the surface here. Now, we do know that with increasing depth, the temperature tends to increase, what is also referred to as the geothermal gradient of the planet. That as you go into the depth, temperature keeps on increasing. Upon a certain level, the temperature starts increasing by almost around 20-25 degrees Celsius with every kilometer depth that you achieve. So the temperature keeps on increasing. Let's suppose at a particular depth, I have certain materials in solid form. Let's suppose at a certain depth. Now, let us assume the surrounding temperature, let's assume is somewhere around 600 degrees Celsius. Okay. Now, here, melting point of the material of the material, let's suppose, is around 650 degrees Celsius. So if the melting point is 650 and the surrounding temperature is around 600, this will exist in solid or liquid. Let me see if we are alive or not. Solid, good. That means we are awake. A few of you have said liquid as well. Okay. So it will be in solid because the surrounding temperature is not as high, right? Now, here there is a pressure which is acting on this particular material due to the kilometers thick rocks which are present. There's going to be a tremendous pressure which is going to be observed, high amount of pressure which is going to be observed. Now let's suppose due to some event or the other, let's assume there is a development of a crack. there is development of a crack-like feature. Now, once the crack develops, meant of a crack or a fault. Now, once this develops, what will happen to the pressure being experienced by the materials? Will the pressure remain the same? Will the pressure increase? Or will the pressure experience a reduction? What do you think? Very good. Oh, any of us, all those who have said that the pressure will increase, any of us, if you can volunteer to enlighten all of us that how the pressure is supposed to increase that there? Pressure is what? Pressure is basically the total force exerted by the materials overlying on top, the total weight that they are experiencing, the total force that they are exerting on the region. So that is the pressure. So if there is a development of crack, obviously the pressure will reduce. Okay, the pressure will reduce significantly. Asha, my dear friend, you have been asking the same question repeatedly. What is the meaning of tremendous force? Tremendous means something which is very large, very high, very huge, very great in quantity. That is tremendous. You apply it with pressure, tremendous force, tremendous or good activity, anything you can use it. Tremendous is not a term of geography. This is a simple term of English. So here, pressure decreases. In case you are unable to visualize what is pressure, so think about it. Let's suppose I keep any of these. Let's assume I keep this particular bottle. Now this will exert some pressure on my hand. Significant amount of pressure will be exerted on my hand, isn't it? So keep anything on your hand. Your hand will experience a pressure. Now if let's suppose this bottle develops a crack, the amount of weight that my hand is experiencing, that will reduce or not? Easily it will reduce. So that is where the pressure reduces. Now, with the reduction of pressure, why the pressure has reduced? Because there is a crack developed. So the weight will be not experienced to the same extent. Now, once the pressure reduces, what happens to the melting point of materials if you reduce the pressure of that region? What do you think? What happens to the melting point of any state of matter once you reduce the pressure? Very good. Okay. Melting point will also end up reducing, right? Melting point reducing means it will easily then liquefy even at lower temperature. Remember the discussion that we had with the aspect of the solid core, where we discussed that the inner core is solid because the pressure is so high that it cannot melt. So if you reduce the pressure, it will readily melt, isn't it? So with the reduction of pressure, there is reduction of melting point of melting point. Now, here the surrounding temperature was 600 degrees Celsius. Let's assume the reduced melting point let's assume that the reduced melting point comes around 580 degrees Celsius. Earlier it was 650. Now, because of reduction of pressure, now the materials will be able to melt easily. So let's assume that the melting point has reduced to 580 degrees Celsius. Then what will happen? Here the surrounding temperature is already 600. So the materials will start melting. And once the materials start melting, they will find a passage through the region of the cracks as well. And that is where the eruption will happen. So that is why, in very rare circumstances, sometimes due to development of large and deep cracks, there can be a volcanic eruption which can happen, provided that the melting point reduces sufficiently. It could also have happened that the melting point would have reduced to 620 degrees Celsius. Still no eruption would happen because the surrounding temperature would be 600, right? So melting point could have reduced, but only in cases where the melting point reduces beyond the surrounding temperature. That is when materials will melt and eruption will happen. Okay, so development of a crack or a fault, that leads to reduction in pressure, that leads to reduction in melting point. Now, if the reduced melting point is lower than the surrounding temperature, materials will melt and eruption can happen. Okay, that is how an eruption can eventually happen. Now, then, after this, we come to the classification of volcanoes based upon the various different types of landforms that they end up creating. Because when the volcanic eruption occurs, you have a variety of different types of materials which are thrown out, and those materials will start to accumulate. But then, different materials thrown out means they will accumulate in different methodologies as well. They will accumulate and solidify in different shape as well. Various different areas will experience different amount of pressure as the molten materials are coming out. So that is why you have the classification of the volcanoes as cinder cone, stratovolcano, or what is referred to as the composite ones, the shield volcano, lava domes, and you also have what we will study again as the fissure that we have already taken a look into. That is your fissure volcanoes. You also have calderas. That is something we will study later. So, in all this, it is the eruption and the frequency, the type of eruptions, etc., which end up shaping the landscape of that region. And it is based on that landform which is created that you have this classification. Cinder cone. Anywhere that you find the term cinder, that is always associated with fire, isn't it? Anywhere that you find the usage of the term cinder, it means fire. So, cinder cone eruption is a kind of eruption which doesn't create very high mountainous landforms. It will lead to the exit of molten materials. The molten materials will start solidifying immediately in the vicinity. They will develop a kind of a conical feature, not more than 1000 feet or to 1200 feet at maximum. There will be a crater developed at top, the volcanic crater that you have. So overall, this is what is referred to as a cinder cone. First of all, take a look at the image here. So here the molten materials, they are thrown up into the atmosphere, and then they start accumulating around the volcanic vent, and that is how they end up developing a conical feature. So they occur when particles and blobs of lava are ejected from the volcanic vent, and it is blown violently into the air, and the pieces rain down around the vent. Over time, it builds a kind of a circular or oval shaped cone with a bowl shaped crater on top. So crater is what? A kind of a depression. So why is there a crater which develops here? That crater is developed because consistently the molten materials are thrown up and they will solidify surround in the surrounding areas. So in the crater region, you will still find the presence of solidified materials. In many of the cases, molten materials will be accumulated in the crater itself before they start to solidify. So they rarely grow to a size of 1000 feet and more. Their size is generally less. Crater is a kind of a depression, any depression that you have. When you take a look at the moon, you find many craters there. Upon the detailed look of the moon, you find many craters. What are craters? Craters are depressions which are present. Okay. Now, then we have what is referred to as composite volcanoes or stratovolcanoes, and these are some of the largest volcanic landforms that you will come across, where the height is going to be quite significant. Now, they are referred to as stratovolcanoes. The term is derived from the word strata. Strata means formation of layers. So here, the volcano that you will find, the landform that you will find, will be very extensive because you will have the layering, right? You have a significant layering. So the size becomes very large. Yes, all the volcanoes will have a crater, or all the volcanic eruptions will have a crater. So size is very large. Why? Because of layer wise formation of solidified materials. So, for example, take the case of Mount Aconcagua, Mount Cotopaxi, Mount Fuji, then take the case of Mount Pinatubo. All of these indicate a kind of a composite volcano. These are very large. How are they created? So, here also eruption happens, but here the type of materials which are actually produced in every eruption, that tends to vary or frequently tends to vary. Understand that all the molten material or all the magma that is present, that doesn't have the same kind of flow associated. Some types of magma, they will flow like water. That is how fluid their flow will be. Some types of magma, they will move like chunks, blobs of semi liquid, right? Like jelly that you would have observed in your childhood days. So some of them, they will represent a kind of a jelly formation, some of them will flow like water. So it depends upon the minerals which are present in the magma. Without going into the depth of it, you have various different types of eruptions, andesitic eruptions, basaltic eruptions, etc. But then, just to tell you the overall view and a brief overview, that the materials present in the magma, including materials such as silica, they end up determining the flow factor. So let us assume in any particular region, initially there is, through the magma chamber, let's suppose this is a magma chamber. Initially, you have, let's say, a kind of a jelly, viscous, as it is referred to, viscous magma which comes out. Viscosity refers to the ability of any fluid to flow. If a fluid is able to flow easily, it is referred to as non-viscous, or viscosity is low. For example, if you have a jar of honey, if you have a jar of water, you start pouring both of them at the same time. Both of them will take different times to empty the jar. Water will be emptied much quickly because water will have a flow, whereas honey will have a slower flow in general. So, when you have, let's suppose, a viscous material which is thrown out, now that viscous material, let's suppose it exits here with a significant pressure, and then it starts depositing, and it deposits here around the vent. In between, it will have the crater and volcanic vent and so on. Now, after that, during this eruption, when it is happening, there will be huge amount of ash also, volcanic ash. Volcanic ash consists of various different types of elements. Now, that volcanic ash, whenever there's an eruption, that volcanic ash can travel for many kilometers carried by the wind, but overall it will get deposited. So, that volcanic ash gets deposited in the surroundings. Let us represent volcanic ash by a different coloration. Let's use black if that is visible. Let me know if it is visible. Is it visible? No? Okay. Okay. So let's assume here you have deposition of volcanic ash. Now, by the way, just to give you some amount of trivial information associated, now this, whenever the volcanic eruption occurs, this volcanic ash that travels a large distance and that gets deposited in many of the areas, so it immediately reduces the visibility. And when it starts getting deposited on the leaves of the plants, that is where it is able to close down all the pores of the leaves, and that is where photosynthesis and air and gaseous exchange that is inhibited and the plants will die. Having said that, if that volcanic ash is applied in very micro quantities, very small quantities into the soil fertility increases. Why? Because this ash will consist of many different minerals. So if applied in very small quantity, it can also always lead to an increase in soil fertility in the long run. Okay. Now, here, after that, let's assume after some time, as here the plate movement was happening and there is further melting of the materials, let's suppose basaltic eruption has happened. In the sense, basaltic eruptions are the one which will flow very easily, where it will flow like water almost. I will show you the picture of how the basaltic lava behaves. Let's suppose there's a basaltic eruption. So it erupts, flows very easily, gets deposited on top. It gets deposited on top. Right. Then suppose again after few years, few hundred years, few, let's say 500 years, 700 years, there is another eruption, massive eruption, which again releases a kind of a viscous material. And that viscous material again gets deposited. So what do you observe here? You will observe that the landform not only is increasing in height, it is also increasing in its dimensions in terms of the width that is associated. Right. Its dimension is increasing quite significantly. And that is where it creates a very large size of a volcanic landform. And that is what we refer to as the layered form or the stratovolcanoes, what is also referred to as the composite volcano. Now, after a long period of time, when subsequent amount of these depositions have happened, overall, you will observe that this will also solidify. This particular portion, it will solidify, isn't it? Through all those thick deposits, it will solidify. So for the molten materials now to be able to break through that entire plug, it will be very difficult, almost impossible to break through, let's say, 1 kilometer, 2 kilometers of solidified rocks. It will be very difficult. So the molten materials in those cases, they use the weaker portions, any cracks which exist. Through them, they will start escaping from the sideways. So through any cracks, any weaker portions that you will observe fresh eruption happening in this area or this area. Now, this eruption is initiated by the same magma chamber. It is initiated by the same area, but the point of eruption is different. So these are what are referred to as parasitic volcanoes or parasitic cones. So this is what is referred to as parasitic cones. Because they are fed by the same magma chamber, but they have a different point of ejection. Hence the name parasitic cones overall. Example of this, take the case of Mount Shasta. having a parasitic cone. Shasta has a parasitic cone that is referred to as Shastina, right? Then various, even Mount Pinatubo, Mount Fuji, all of them can be taken as examples here. Okay. Now, that is basically how the composite volcanoes can get created. So basically here you have one, immediately when the eruption occurs, molten materials will get deposited, then they will solidify as slowly and steadily a layer of ash will get deposited, that will also solidify. Then after that, let's suppose another eruption occurs, that will also solidify. So you have the layering which is formed, and due to different types of eruption which occurs also. Then you have what is referred to as a shield volcano. Now, shield volcano, when you talk about, this is a kind of a volcanic eruption where the magma or the molten material or the lava which is thrown out, that is very fluid. That flows very easily. That has got a flow like water. Because the magma in this case is basaltic in nature. It is rich in iron and magnesium. It has got a flow like water, right? So what will happen? From the region of the vent, it will start spreading, it will start flowing very easily. So whenever you have a vent like this, let's suppose a vent which is like this. Now, if the molten materials are able to flow very easily, they will spread over a larger area, isn't it? They will spread over a very large area, and that is how they begin to solidify. Now, eventually, they will form a feature which is almost plain, consisting of hard rocks, obviously, igneous rocks, but almost plain. Why is the name shield given? Because you would be aware of the shields which were used in battle. You had the swords and the shield. Shield was a protective armor. So the shield basically had a kind of a very simple shape, featureless shape, with a very simple gradient that they had, right? Shields would be used everywhere in the battlefield earlier. So it has got that kind of a shape associated with very little gradient, almost flattish with a kind of a curved feature. That is a shield. Example of this, example of this, you have the Canadian shield, the earlier one, right? Then you have the Deccan shield. Presently, if you observe the kind of eruption which is being noted and which is being experienced in the region of Hawaii, now the Hawaii eruption in general represents this kind of, because in Hawaii also you have that creation of a large shield, and because it is a basaltic lava which is coming out. So this is also sometimes what is referred to as the Hawaiian kind of eruption, sometimes also referred to as Hawaiian eruption. Yes, Mauna Kea, Mauna Loa, they can be considered as examples. Now, here, in the case of the shield, the formation is something which happens due to the fluidic lava. Fluidic lava spreads over. And here, which kind of lava spreads over? You have basaltic lava. Now, think about it. You have a kind of a magma which flows very easily. So, for the exit or the eruption of those materials, will you need an explosive eruption, or can a non explosive eruption also lead to the exit of these materials which can flow easily? What do you think? The eruption in this case, will it be explosive? Will it be non explosive? Very good. So, here you will observe it is a non explosive eruption. Why? Because for this you don't need an explosion to push the materials, because the materials can flow very easily. So you have fluidic lava flows, and they have gentle slopes, and they are built by effusive eruption. Effusive means non-explosive. Okay, non-explosive. Very good. Now, here the materials or the magma is absolutely fluidic. Now, let us come to a type where the magma is very, very, very viscous. Viscous means it is unable to flow at all. So, in those cases, what you will find, if you can visualize this, this is what is referred to as a kind of a lava dome. This is what is referred to as a lava dome. So, Hawaiian eruption is the shield volcanoes that are created. They are also, so you have a classification of volcanoes even based on the eruption style, right? Again, not relevant for your general studies, but you have the classification based on the eruption type. You have the Strombolian, you have the Pelian, you have the Icelandic eruption, you have the Hawaiian eruption. So that is the classification on the eruption type, how eruption happens, what kind of materials are thrown out. So the current classification that we are looking into, that is based upon the landforms created. So similarly, you have another classification. So just to give you an idea, that Hawaiian eruption, shield eruption is also what is referred to as Hawaiian eruption. Okay, right? Now, here, let's suppose you have this as the ground surface. Let's assume here is where you have the magma chamber, right? And this consists of very viscous magma. Very viscous means unable to flow at all, like a jelly of sorts. Now, this magma, it will emerge and it will start solidifying here itself. It doesn't have neither got enough uh, kind of explosive power to fly up into the sky and settle down around it. It simply starts accumulating around. So this creates solidified dome shaped structure. Okay, it ends up creating a solidified dome like structure. And then that is where it solidifies after some time. Let's suppose there has to be a fresh eruption. Fresh materials, they will come from the air and the dome will expand on the outwards. Dome will expand on the outwards. So this will never have a very large dimension. It will have a significantly smaller dimension in terms of the landform which is created. Amongst all the various landforms that we have seen, this will be the one which will have amongst the smallest dimension created as the landform. Okay, it is not like a marsh. It does appear like these are your solid hardened rocks. These are your hardened igneous rocks. Okay, so that is your lava dome. Now, let us come across the interesting one, and that is a fissure volcano. What is the meaning of fissure? Fissure ends up representing a large crack. So sometimes, due to the conditions of a transform movement or conditions of a divergence of plate, where the plates are simply moving apart, where the crust is getting broken and newer crust is created, very, very large cracks are created on the Earth's surface. And through these cracks, molten materials, they start coming out and they spread out. Now, when this kind of eruption happens, again, use your brain. Will it be an explosive eruption or a non-explosive eruption? What does the logic tell you? Beautiful. It will be a non-explosive eruption here also. Because why? Because already the land is paving way. Already there is a crack which is created. So when you have such large cracks in the image, I'm sure you will be able to see how there is a very, very large crack which is created. Now here the example can be taken of the very famous Laki eruption. Iceland is one of those areas where this eruption frequently occurs. Can you think of a logic why Iceland experiences this eruption very frequently? We have discussed about it already. I want to see whether we are aware of it or not. Good. Very good. Because it is present on a divergent plate boundary across the mid-oceanic ridge. That is where the land automatically is moving away. So that is why you have such kind of eruption very frequent in Iceland. So here the example can be taken of the Laki eruption. Laki eruption, which occurred in 1770s. Now, in that eruption, it is said that a crack around 37 kilometers opened up across the surface. 37 kilometers long crack. Imagine the diameter of the city that you are living in. In many of the cases, it would be lesser than 37 kilometers. So that long a crack developed, and molten materials, they start exiting. It is estimated that close to around 96,000 to 1 lakh kilometer cube. Understand, 1 lakh kilometer cube, how much that is. That much amount of molten materials were ejected by the lower portions of the planet into the Earth's crust and above the surface during that Laki eruption. It continued for consecutive years altogether. So that is what is a fissure eruption. Laki is in Iceland. This is in Iceland. Okay. So this crack will develop. Why? Because of divergence of plates, because of transform movement of plates anywhere, this crack can develop. So you have two examples of them. One is Laki eruption, another is Trevera eruption. This happens around the region of New Zealand. That is where the Trevera eruption is observed. So observe here that you have the opening up of a large crack and you have molten materials which spread over. So these volcanoes are formed due to the slow upwelling of low viscous, which is fluidic. Low viscous means fluidic magma along a long fracture and fissure. The resultant lava is spread over a large region of the ground surface. This is what is also referred to as Icelandic type of eruption. Where? Why? Because it is experienced mostly in the region of Iceland. Okay. So we have seen what is a cinder cone. Cinder cone is a simple eruption where it accumulates around the region itself, around the vent itself, largely consisting of a kind of a viscous lava. It will keep on accumulating. It won't have much greater of a height. Large heights, that are stratovolcanoes, where you have layers of deposits of lava, ash, lava, and followed by ash. So that is a stratovolcano. Then we have seen that how in stratovolcanoes there is development of a parasitic cone. When the molten materials, they find it very difficult to exit from the central portion, they will exit from the sides. That is a parasitic cone. Then we have seen what is a shield volcano, where the materials spread non viscous lava. It spreads out very easily like fluid, and it solidifies in a kind of a shield like proportion. You have the Capwal Craton, or the African shield. You have the Canadian shield. You have the Deccan shield in India. These are the examples of shield volcano, which is also referred to as Hawaiian eruption. Then we have seen the lava domes, where the very viscous materials, they will solidify immediately around the vent, and they won't have a great height or any great feature for that matter. And slowly and steadily, when fresher eruptions will happen, it will simply grow on the outside. And then you have the fissure eruption, where the land parts way. Why does it part way? Because of divergence of plates, or there's a large crack created due to transform movement of the plates. And then you have in these long cracks eruptions happening across the crack, which is the fissure eruption. Okay, so that is the type of eruptions that we have seen based upon the landform. Now, here, are we going really fast? We have covered only 5 to 6 slides since the beginning of the class. I think we are going really slow. Okay. We are rather going very slow. So any of you who is alleging that we are going fast, think about it. If we don't follow even this speed, then maybe in 24 modules we will be covering only geomorphology. You can forget about Indian geography, oceanography, everything that you can forget. Okay. So anybody who feels that we are going fast, please point out. If I find that a significant chunk of you indicate we are going fast, we will slow bind further. But I think we are going typically slower, right? Janvi, example of fissure volcano we have seen. This is the Laki eruption of Iceland, Travera eruption in the case of New Zealand. These are examples of the fissure volcanoes. Okay, and in the meanwhile, in a parallel universe, I have another question, that which part of geography is most important for prelims. Let us first of all cover geography, my dear friend. As of now, we are finding it difficult to set up a pace in this subject. Let us cover at least the chunk of one particular unit, at least geomorphology or climatology. Then we will decide which is important or which is not important. Okay. Example of composite volcanoes. Composite volcanoes are examples. You can have the case of Mount Shasta, Mount Rainier, Mount Hood, Mount Fuji, Mount Kilimanjaro. All of these are your examples of composite volcano. Travera, I have said multiple times. New Zealand. Okay, do you guys want a greater amount of written text in the PPT? I will put that in if you want. Is it that once you are not finding the portions which are written, you are finding it, you are basically feeling uncomfortable? Okay. So you need written text in the PPT. Okay. So that you can close your eyes, and after that, you can simply rectify the written text. I'll do one thing. From the next portion, we are basically going to increase the amount of written text, and I hope that nobody gets uncomfortable and nobody has a complaint that the faculty is simply reading through the PPT. I will put in the as much amount of written text as possible. A cinder cone. Okay, what is cinder? Cinder cone is base. What is? How many of us we have no clue what is the meaning of cinder? I think majority of us who are finding it difficult, we are finding it difficult because we don't know what is the meaning of cinder. What is the meaning of cinder? Okay, cinder is basically anything associated with fire. That is where cinder is used. Incendiary remarks. You would have studied in the Supreme Court judgments as well that incendiary remarks. What is the meaning of incendiary? Something which can spark a fire. So, cinder is associated with fire. And when we talk about cinder cone, and everybody listen to this, I don't want you to raise this question again because I did not take your name. So, when we talk about cinder cone, in the case of cinder cone, you will observe that there is an eruption which happens, and the materials they settle down around the volcanic vent, but they don't gain enough amount of height. And there it is a simple volcanic eruption which doesn't have enough of a height, where you can have basically the basalt of fluidic, non-fluidic lava as well, but mostly you have a non-fluidic lava, a viscous lava which accumulates around the surrounding, and that is what is referred to as a cinder cone. Is that understood? Okay, right. And why fissure volcanoes are mostly seen in Icelandic region? Fissure volcanoes, what are fissure volcanoes? When a large crack will develop, whenever you have a large crack which will develop, that is something which is going to initiate a kind of exit of materials throughout the crack, like you see in the image. Now, Iceland is situated on the mid oceanic ridge, where you have already the divergence of the plates which is experienced, that is where Iceland is situated. So that is where you will observe majority of this fissure volcano happening. You will also observe fissure volcano very prominently across the entirety of the mid-oceanic ridge. Is volcano found in sea areas? Yes. I still could not comprehend why reduced melting point vis-a-vis surrounding areas causes eruption. Because if the melting point reduces and if the melting point is lesser than the surrounding areas, won't the materials melt? The materials will melt. And for volcanic eruption, what do you need? Don't you need the basic requirement or the basic component of a volcanic eruption is what? Molten materials. So that is why you will have eruption. Okay, see Lakshmi, you are asking a question. First of all, you asked a question: is volcano found in sea area? Is volcano now your next question is volcano found in desert area? So if you have that kind of a question, frame it in the same one, that is volcanic, can it be found in water, can it be found in volcanic eruption can happen anywhere. Anywhere it can happen, depending if the present or if the circumstances are ideal or not. Volcanic eruption does not depend on whether the outside material is a desert, or whether you have grown crops there, or whether there are people living there. Volcanic eruption doesn't have a mind of its own. It only looks at where there is a crack, where if there is availability of molten material, it will erupt, it will emerge. Okay. About mid-oceanic ridge, kindly look at the recordings. It is available in detail, the discussion. Why Indian subcontinent don't have any volcano except Andaman? Why? You tell me. In India, in the case of Indian continent, do we have the continental convergence or not? So in that case, in the case of continental convergence, do we have a volcanic eruption? Let me know. We don't have. We have looked at the reason as well. I have written in the PPT itself. Okay. Volcanoes give rise to islands, right? So in that way, does Fisher volcano pave the path between the two? It can end up creating islands, like Iceland is one of those. Why melting point reduces with the reduced pressure? What is melting point? Understand that. What is melting point? This is like elementary science, very basic science. So when we talk about melting point, it is when a solid changes its shape to liquid, when solid gets converted into liquid. That temperature is referred to as melting point. Now, if let's suppose there is a solid on all different sides, if I attach significant amount of pressure here, will the solid get converted into liquid regardless of how much temperature you provide? So if the pressure increases, the solid won't get converted into liquid. Why? Because for getting converted into liquid, you need expansion in volume. Here you are not allowing any expansion in volume. So the solid will remain as it is, regardless of how much temperature that you attain. That is why the inner core is in solid state. Now let's suppose you reduce this pressure. Will it melt readily or not? It will, because it will be able to expand. So when the pressure is reduced, that particular material gets a scope to expand easily. And that means it can melt at an easier or a lower temperature. Okay? Is that understood? Can we get prior warning of volcanic eruptions? Maybe 1 or 2 days prior, that this region can experience an eruption, but not significantly forward. Shield volcanoes create plateaus as well. Yes, Anubhav, they can create. Rajan, but the thing is, why the magma come outside from the inside? It is the pressure by the gases. That is what I have repeated multiple times, my dear friend, that the gases which are present along with the molten materials, they will bring the molten materials upwards. If those gases are not present, then the molten materials will start solidifying where they are. Okay. Why does the Deccan Plateau region had a fissure volcano? Deccan Plateau did not have a fissure eruption. It had a hotspot kind of an eruption. Craters can be found wherever you. Crater is what? Crater is a kind of a depression. So wherever, in the case of, let's say, there has been an asteroid hit, there is a meteor hit, collision, it will create a crater. Lonar Lake in Maharashtra is a crater lake. Okay. Is the volcanoes called Kamaljeet? Is the volcanoes give cause damage like earthquakes? So whenever you have the volcanic eruption in the immediate vicinity, everything is destroyed because the molten materials, they start spreading and they will solidify. Okay. Why does okay, that is where can I, how far does a volcano go? Volcano does not go when it explodes. Volcano will be there itself. The materials can move. The materials, when it is carried out by the wind, it can move away many kilometers. And the most explosive eruption that we had in the last couple of years was a Tonga eruption, where the cloud which was created, that went as high as 100 kilometers into the atmosphere. So it can go as high as around 80 to 100 kilometers. Tephra basically refers to the broken fragments of rocks, etc. That is what is tephra. What is the meaning of Icelandic eruption? It is another name of the fissure eruption. That is what is referred to as Icelandic, because this kind of eruption is frequently observed in Iceland. Okay. Does pressure solidify or melt in the magma? Question is not clear. What is the difference between shield and... So shield volcano creates a kind of a dome-like feature. There's no difference. Is volcanic eruption considered as a natural disaster? Obviously, yes. Can it be said that volcanoes make newer crust? Sometimes, yes. What is the meaning of a fissure? Okay, fissure. Okay. See, guys, you will be needing, many of you will be requiring an improvement in your English vocabulary as well before you write the mains paper. Please don't take it in a negative manner. Take it as an important feedback. You will be required, many of you, to improvise some amount of your English vocabulary skills as well. Okay, and will this be covered in depth again after? What is the depth that you want to know? Please ask a question. For general studies, this much is required. As we are discussing, we'll be discussing caldera, mantle plume, hotspot. That much also you will not find in many of the books, trust me. How can there be a man-made volcanic eruption? There is no man-made volcanic eruption. When magma will melt, when melting point, when will magma melt? When melting point is higher, or when the surrounding temperature is equal or around melting point, it will melt. If the melting point is high and the surrounding temperature is also high, why won't it melt? So when the surrounding temperature is around the melting point, it will melt. Okay. And I won't be answering any of the... What are the aspects of volcanic eruption? In the sense, what do you mean by the aspects of volcanic eruption? How seismic activity shows molten materials included in lava chamber, because the P waves will be able to travel through the gases and the liquids as well, whereas the S waves won't be able to travel through it. So that is how you know whether it is a liquid molten material is present or not. Fault creates a pressure reduction, because fault is what? A development of a crack. If there is a large rock which is placed on your hand, it will exert some force. But let's suppose there's a crack which develops on the rock. The amount of force exerted will reduce suddenly, isn't it? Yes, it is important for both pre and mains. So many of you are asking very random questions, and then you cannot say that we are moving slow. Okay, these are very, very random questions that you are asking, and it is just for the sake of asking questions that many of them are asking this. So, can movement of transform plate boundaries create fissure? Yes, it can. Does the magma will melt the cap of hard igneous rocks in the vent? Yes. Anubhav, your question was that whether the shield volcano will be observed in the case of the islands. They can. Learning notes will be sufficient? Yes. PPT will be sufficient? Yes. Will eruption damage ozone layer in case it punctures through it? Yes. And meanwhile, in a parallel universe, is it centrifugal force? Then why crust move towards equator? Although centrifugal force acts away from the center. My dear friend, that is what he proposed. Alfred Wagner, that is what he proposed. This reason that he cited was incorrect. That is why continental drift theory was rejected. Okay. I have said this in the previous session also. So whenever you have these types of doubt, you can always refer to the recorded videos. Okay. Now we come over to the portion of calderas. Okay, let's do one thing. Let's take a break before that so that we get back into the serious mood again. So we take a break and we'll be coming back in 15 minutes and then we will continue. And for all of you, I would suggest have a pinpointed answer. We will be able to solve it much easier rather than having a very vague answer that explain about the aspects of volcanoes. So I am not expected to write the answer in 250 words in the examination. If that is your expectation, please moderate your level of expectation. Okay. So have a pinpointed question. Wherever you have a question, don't worry about it. Have a pinpointed one. We'll get to it. Okay. What will happen if the melting point is lower than the surrounding nature? It will melt. The material will melt. Okay. Is there a differentiation between the dormant volcanoes in terms of no? There is no differentiation. Okay. Let's take a break and let's be back. Will the eruption take place? If it can break through the crust, yes. Roshan, Roshan, 11th and 12th NCRT is more than sufficient. Read that. Is the frequency of volcanoes reducing? Yes, as compared to the earlier times of the planet Earth, yes, it is reducing. Or in the phase of the volcanic eruption. Does not mean there cannot be a fresh eruption happening after that. But generally, it is created in the last phase of the volcanic eruption. And here, one of the important aspect is that the eruption has to be explosive and the magma chamber needs to be emptied in order to observe the creation of a caldera. Let me write it down first of all. So here, when we talk about a caldera, these are landforms landform created in the last phase of the eruption. Here, the requirement when it comes to the formation of a caldera. So the requirement is magma chamber needs to be emptied and also you need to have a very explosive eruption. So let us understand what happens and how is it that the caldera is created. So when we talk about, let's say, a kind of a volcanic landform, okay, where you have a significantly larger magma chamber, a significantly larger magma chamber, and let's assume that on top of the magma chamber, this is the kind of a landform which exists due to multiple different eruptions which would have happened in the past. This is a kind of an eruption or the landform which has been created here. Let's assume. Now, if there is a very explosive eruption happening, let's suppose the eruption is very, very explosive in nature. Now, in those cases, will you observe a pressure exerted on this particular landform in case there is a very huge explosion? There will be pressure which will be exerted, isn't it? So, on this landform, you will have a high amount of pressure which will be exerted. Now, when the pressure will be exerted, is it right to come to a deduction that there can be a development of a large featured crack here? A large crack will be developed, isn't it? A large crack will be developed because of the nature of that explosive eruption which has happened. So, here, a very explosive eruption. So, a large crack is created. Created. Then, after that, when you have such a large crack which has already been created, that means that is a weak portion across that entire landform. Now, the magma chamber, let's suppose the final materials which were present, the final molten materials which were present, all of them have been thrown out in that last phase of explosive eruption. So now the magma chamber is emptied, right? So let's assume the magma chamber has been emptied. How will it be emptied? All the molten materials are thrown up. All the gases, molten materials are thrown up in that phase of explosive eruption. So once that magma chamber is emptied, so you have a kind of a vacant space. And on top of that vacant space, you have a large landform which exists. So will that vacant space be able to handle all that pressure and weight being exerted from top? Or will that vacant space crumble within itself? What do you think? Will it be able to withstand the weight, or will that weight in a way lead to the crumbling of the landmass because there is nothing underneath? It will crumble, right? So here, basically, when you have creation of such a situation where the magma chamber has been emptied, so the overlying weight of it, it simply subducts and subsides. So the overlying weight, that will undergo a kind of a subduction from the region around the crack. So what you are left over is a kind of a very large depression where the top portion subsides due to empty magma chamber. Now, generally it is observed such kind of very explosive eruptions, they are generally to be observed in the areas where you have an oceanic convergence or any kind of oceanic plate is involved, because that is what will end up producing so much amount of water vapor that a pressure will be induced which will create an explosive eruption. So in these areas where you have an oceanic convergence happening, generally oceanic regions will lie in the surrounding region as well, in the surrounding vicinity as well. So that oceanic water ends up in many of the cases filling up that gap. Sometimes when, let's say, it is happening over the land area, in that case you will have the groundwater eventually which ends up filling up that region, creating a very large crater lake of sorts. So this landform which gets created where the top portion has gotten subducted in the last phase of eruption due to the emptying of the magma chamber, and the empty magma chamber means you have a vacant space which is unable to handle that particular weight anymore. So in those cases what you have is creation of a large caldera. Example you can cite of Crete in Greece, then also Tonga eruption. Okay, so that is basically here when we talk about the creation of a caldera. So in the case of the Tonga eruption, Tonga is where in the region of South Pacific. So you had basically two various different vents or two volcanic landforms created in very close vicinity. You had the Hunga Tonga and Hunga Hapai. Now, in the last eruption, which was very major, that happened on 15th of January 2022, and in that large, massive eruption, there was a significant amount of material which was thrown out. The magma chamber was emptied, and there was the entire depression which was created. So, this is what is referred to as a caldera. Now, in the region of a caldera, generally because it is accompanied with the emptying of magma chamber, no frequent eruptions will be observed. Having said that, in the future, there can always be a possibility of a fresh eruption if the magma chamber is again recharged or if there is creation of molten materials again. There can be a fresh eruption which can happen. Okay, so I will recap it very briefly. When we talk about a caldera, this is created in certain cases when you have the last phase of the volcanic eruption which is observed. And in those conditions, when you have a very explosive eruption which happens, so in those cases, you have, due to the power of the explosive eruption, large cracks develop in the landscape. And then those weaker points, will develop a crack. Accompanying that, the magma chamber is also empty. Now, the empty magma chamber means it won't be able to withstand the weight of that overlying landform. So, that landform will crumble, it will cave in, it will subside, and that creates a caldera. So, the image that you see on the screen, imagine at one point of time, this would have been a volcanic landform somewhat like this, where the top portion has simply crumbled down, and what you have is a creation of a large caldera lake, right? Large caldera lake. Okay. So, while every volcano will have a kind of a crater, but that crater is nowhere compared to the formation of a caldera lake, because a caldera lake is going to be much, much larger. And the volcanic crater that you observe, what we saw in the case of the cinder cone or stratovolcano or anywhere else, that is simply because of the eruption methodology. Here, material has actually caved in, the material has actually undergone subsidence. Okay, so that is the aspect of caldera. How does magma chamber get emptied? Because if all the materials are exited, then it will get emptied, and magma chamber gets materials from below. Magma chamber does not get material from below. If you have that conception that magma chamber is provided by, where does the liquid or the fluid or the molten material in magma chamber, where does it come from? Let me see if we are aware of that. Where does it come from? Not all extinct volcanoes will create caldera. No, it is basically created, the molten material in the magma chamber is created due to the plate movement, due to the convergence, and that is where in the region of asthenosphere, as the plates will move, as the plates go below at a particular depth, they will start melting in certain portion and they will provide the molten material. Okay, it is not as if somewhere you have a pool of molten materials kept and they keep on erupting. If that would have been the case, volcanic eruption would have happened everywhere, but they are restricted in certain places, isn't it? So that molten material is supplied continuously by the melting of the plates due to the plate movement, which is generally observed. Okay, now how it crumbles down, because here you have the empty space which won't be able to withstand the weight of the large landform above, and because the landform has developed cracks due to the explosion, so that is why the central portion will simply cave down. In any landmass, take a aspect of it, in any landmass, if let's suppose this is the land, and if you have a large gap underneath which is vacant, what will happen? Won't the landmass simply sink and subside, isn't it? So that is how you have the creation of that caving, or that subsidence happens because of that. Where does the water come in? So in general, these calderas, they are created around the region of the oceanic convergence. So that is where you will have a presence of lot of seawater from the surrounding region. In both these cases, the seawater from the surrounding regions, they have filled in. But in this case, which represents Mount Oregon or the Oregon Lake in general, so here the seawater did not come in. You had the water being channelized from the surrounding groundwater area because the central portion subsided, exposing the capillaries to the groundwater supply that filled up the water. Okay. Now, then we come over to the portion what we refer to as a mantle plume. Now, before talking about mantle plume, what is the meaning of plume? Because I see that many of us, we are getting confused in the meaning itself. So what is the meaning of plume here? When you come across the term plume, what does plume signify? No, it does not mean deposit. No, no. Okay. Neha, you are partially correct. Aman, perfect. Okay. Plume is basically any rising column of heat that you have. Generally, a rising column of heat that is associated, that is referred to as a plume. You would have heard about the terminology plume of smoke rose up in the sky, right? So, anywhere where you have a rising column, that is what is referred to as a plume. So, when you burn something, when you put fire on something, you will observe that the smoke rises up. And how does the smoke rise up? It forms a kind of a thin stem like feature and a large bulb like feature on top, and that is how the smoke rises up. So, that is basically a plume. So, a rising column of heat that travels upwards, that is a plume. So, when we talk about mantle plume, what do we mean by mantle plume? So, in the region of mantle, heat is transmitted upwards in the form of a convection current. Now, that heat oftentimes travels upwards in the form of a kind of a plume like feature, and that is what is referred to as mantle plume. To give you the definition so that you get some ease. So it is the convection of magma in narrow columns in the upward direction from the core mantle boundary many of the times, sometimes even from asthenosphere, forming a mushroom shaped cap of the plume. And mantle plume magma is hotter than the surroundings, so it rises. So here, when we talk about the plume and the representation of the plume, from the region of the Gutenberg discontinuity, that is the core mantle boundary, oftentimes you will observe there are rising sections of heat, rising columns of heat. That is what is referred to as a mantle plume. So if I have to elaborate it with the help of an image, so let's suppose this is your crustal portion. Okay, let's suppose this is your moho, and here you have the mantle, Then let's suppose here is where you have the Gutenberg discontinuity, and here is where you have the outer core. Now, we do know that in the region of outer core, we have a significant amount of heat which has been trapped ever since the formation of the planet itself. And what is that heat referred to as? That is what is known as the residual heat. So around this region, you have a significant amount of residual heat which is trapped. Residual heat. Now, as we have already talked about it when we were talking about the convection current theory, we have seen that this residual heat basically keeps on getting supplied from one place or the other. The residual heat consistently is escaping the Earth's interior. Now, as this residual heat, let's suppose, is emitted from some particular region. Now, here, let's suppose the residual heat is coming out from this region. It will melt the materials in the mantle immediately here. Now, that's liquefied portion of mantle that will try to come up, that will try to erupt, that will try to emerge slowly and steadily. As it emerges, what will happen? It will melt the materials upwards. So this, you will have the formation of a kind of a rising column of molten mantle. Okay, here you have rising column of magma due to residual heat. Okay, so that rising column of magma is initiated. Why? Because there is significant amount of heat which is supplied, and it starts melting the portion of material, magmatic material, and those molten materials, they will always travel upwards. Why? Because they will be lighter than your surroundings. So that is why they will start rising up. Now, these mantle plumes can end up having certain impacts. It can end up creating certain impacts. So, if I have to talk about the impacts of the mantle plume, can you think about certain impacts which it will create, these mantle plumes? So, can we say that this mantle plume can give rise to convection current which can initiate plate tectonics or plate movement? Can we say that? Will that be a meaningful deduction? Perfect. So here, can induce a convection current in the mantle which can give rise, lead to plate movements. I hope we are comfortable till here. Now, what about the second impact that it will create? Now, all this molten portion of the mantle which is rising up, in a way, in certain cases, it will also end up recharging and forming the magma chamber, isn't it? In these cases, in very rare cases, if there is a magma chamber or if there is a magmatic eruption here, it can keep on filling the magma chamber. And in those areas, what will happen to the volcanic eruption? Volcanic eruption will be consistent because the magma chamber is always to be filled. Consistently, magma chamber is being filled by the molten materials provided by the mantle plume, isn't it? So here, fills up continuously, up the magma chamber, leading to frequent eruptions at the same place. We can say this, isn't it? So that is what is created by a mantle plume. So mantle plume is initiated why? So mantle plume can be initiated. Earlier it was understood that mantle plume is initiated only in the region of Gutenberg discontinuity, because that is where a lot of trapped heat is there or residual heat is trapped. But later on, it was found out that it can be initiated even in the region of asthenosphere sometimes because of excessive heat produced in asthenosphere in certain areas. So it can be initiated at the region of Gutenberg discontinuity, due to residual heat, or it can be initiated even in the case of asthenosphere. Okay, so these are the places where the mantle plumes can be initiated. Then after this, here, when we have talked about the release of the residual heat earlier while we were talking about the convection current theory, so that release of residual heat, first of all, in any particular place where it is observed, it can continue for hundreds of millions of years, right? It can continue for hundreds of millions of years. In the same region, the residual heat is consistently being released. But it might be possible that after hundreds of millions of years from that region, let's say there is no heat which is released anymore, and from some other region, the residual heat might start getting released. So overall, the position or the location of the mantle plumes, they are considered to be permanent in nature when you consider our own time scale based upon our human lives. So the mantle plumes, their position will be fixed. But when you consider the time period in reference to the planet Earth's time and planet's Earth life cycle, then you will understand that these mantle plumes can end up changing ever so slightly. So that is the characteristic, or that is what is referred to as a mantle plume. Now, wherever a mantle plume exists, that is nothing but a rising column of molten materials, the rising column of the molten mantle, which eventually emerges close to the surface. So it can end up creating plate movements, it can initiate divergence, convergence, transform movement of the plates, it can end up creating volcanic eruption as well. In areas where they will influence the volcanic eruption, they will fill up the magma chamber to such an extent that very frequent volcanicity will be observed. And that creates what we refer to as the volcanic hotspots. So when you hear about the term hotspots, it basically ends up representing any of those areas where, or any of these events where the frequency is higher. Hotspot, right? Hotspot of or a hub of meeting activities where everybody keeps on meeting. Hotspot of crime, where crime is very frequent. So when you talk about volcanic hotspot, these are those places of volcanic events, or those places where the volcanic actions keep on happening repeatedly in the same region for hundreds and thousands and millions of years. Okay, generally you will find that the volcanic hotspots, they will lie above the region of mantle plume, and they leave behind a trail of landforms which indicate about the past volcanicity as well. So let us understand that. So hotspot is a volcanic area on Earth that generally exists over a mantle plume, which witnesses continuous volcanicity spread over millions of years. Okay, so here witnesses volcanic activity for millions of years continuously. Why? As the magma chamber is continuously recharged. Where is the magma chamber getting recharged from? From the mantle plume. Now, this continuous and frequent volcanic activity that ends up creating a trail of volcanic landforms. This creates a trail of volcanic landforms. And that also, analyzing those volcanic landforms over a period of time, this also gives us an idea and information about the direction in which the land is moving, or the direction in general of the plate movement in general. Creates a trail of volcanic landforms. So understand this. For example, let's suppose in any particular region, if this is the land, let's suppose here is where you have the volcanic vent, and then you have a very full magma chamber, significantly full magma chamber, which is consistently being supplied by the molten materials from the region of the mantle plume. Now, initially, if suppose this is the plate, now initially, let's suppose there is a volcanic eruption which creates a landform like this. Now, it is here that volcanic activity or event will be observed. And here, the plates on top of which the volcanic landform is created, those plates will never remain consistently in the same position. Those plates will move in some direction or the other, but the plates will move. So let's assume these plates are moving in this direction. So after few thousand years, what will you experience? You will experience that this particular volcanic landform which was present here, this has shifted slightly, ever so slightly, right? This has shifted ever so slightly. Now, it can happen that it can still be connected to the ancient, or rather the older magma chamber. It can happen in certain cases. And there might be sporadic volcanic events happening here also. But the main volcanic event will happen where? The main volcanic event will happen here. So you have another landform created. But again, after some time, this plate will move. The plate movement is something which is observed. Now, after some time, what will you observe? The earlier two landforms which were created, they have moved further. In the meanwhile, there will be newer eruption here. Right. Again, this will be moving, the plate will be moving because the volcanicity is almost continuous. It is consistently fed by the magma chamber from below. So again, due to the plate movement, let's suppose all of this has moved. Let's suppose. Now, in these areas, no volcanic events are observed anymore because they are now not connected to the magma chamber. But where the magma chamber lies, there can be a fresh eruption. So like that, what you observe is a trail of volcanic landforms as the plate tends to move. So in this image, if you will observe how you have a chain of volcanic events, right? Volcanic landforms. All of them are supplied from the magma from the same hotspot. But then as the tectonic plate on top of them, that is moving. So earliest eruption would have happened here at one point of time. This would have lied directly over the magma chamber. This would have moved. Then further eruption. After again some time, further eruption. And like that, you have the various different kinds of trail created. Why is the land moving? Okay. Because of plate tectonics. Have you attended the session for plate tectonics? Pooja and Gauri, both of you, have you attended the session for plate tectonics? Yes. So there did we see that the plates have been moving? Yes. So if the plates are moving on top of the magma chamber, there can we understand that why the entire plate is moving and why the entire landmass is moving? Can we get the idea of that? Yes. Good. Now, after this, the example of this volcanic hotspot. So when we talk about the example, you can have two examples of a very distinct volcanic hotspot which is prevalent. One of the example is that of Hawaiian hotspot. That is why the region of Hawaii experiences very frequent volcanic eruptions. Then after that, you have the Reunion Island hotspot. Where is Reunion Island situated? In the region of the southern Indian Ocean. Reunion Island hotspot. These are your examples of the hotspots. Now observe how they have created a trail of landforms. So here, when you talk about the Hawaiian eruption, or the Hawaiian hotspot, so mantle plume consistently enriches the magma chamber here. Magma chamber is consistently recharged here. That means always you will have the availability of molten materials. Now here, what you will observe is this is the location of Hawaii. So the oldest volcanoes, they have also been created due to the eruption happening here. That means at one point of time, this landmass would have been present nowhere but here. Slowly and steadily, the landmass would have moved because of the movement of the Pacific plate itself. That is why the landmass would have moved. Now, as the landmass would have moved, the eruption would have continued. Observe here that this eruption happened 5.1 million years ago. This eruption happened around 2.6 million years ago. This eruption happened around 1.8 million years ago. This eruption happened around 1.3 million years ago, zero point 0.8 million years ago. And here, this eruption presently that we see in Hawaii, that has been happening for the past zero point 0.7 million years to present. Okay, so that is basically how this eruption. So observe here the entire Emperor Seamount chain. So here the eruption at one point of time, understand that this region that you see, it was present here, but the Pacific plate has moved. The Pacific plate initially would have moved in this direction and then in this direction, or vice versa could also have happened, that initially it would have moved in this direction and now it is moving in this direction. That is why it has created a trail of islands and a trail of volcanic landforms. All of them have been created from the same Hawaiian eruption. We'll study in the portion of the Indian geography as well that when we talk about the creation of Deccan Plateau has also been created due to volcanic eruption. But that eruption was initiated when India was very much over the Reunion Islands. It was the Reunion Island eruption which created those landforms. And in fact, many of the island chains that you observe to the south of India in the region of the Indian Ocean, they have also been created due to eruptions of the landmass which have happened to lie above the Reunion Island volcanic hotspot. Okay, so that is basically about the volcanic hotspot. Now, then we come to the intrusive volcanic landforms. What do we understand about with the intrusive volcanic landforms? Every volcanic mountain contains mantle plume? Absolutely not. Absolutely not. So, when we talk about intrusive volcanic landforms, intrusive means something in the interior. So we have already talked about the fact that when you have the pressure induced by the gases in the magma chamber, when the magma chamber will have the presence of gases, that will add to the pressure which will push the or pull the materials to the surface. Many of the times it happens that the crust is so very hardened, thick, or maybe let's suppose consider or is considered of a consisting of a mountainous area, and there is not enough pressure, the molten materials might not be able to erupt through to the surface. The molten materials might try to come to the surface, but in the process, let's assume that the molten materials have spread in between the layers of the rocks. They have spread out in certain sections, right? And they would have solidified. Maybe the entire magma chamber in itself has solidified. Now, once they solidify, they form what is referred to as intrusive igneous rocks, isn't it? They form what is referred to as the intrusive igneous rocks. Now, these are referred to as the intrusive volcanic landforms. Now, how do we come to know whether there has been a solidification taken underneath the planet's surface or the Earth's surface or not? So, over a period of hundreds and thousands and millions of years, let's suppose this has solidified. Over a period of hundreds and thousands and many hundreds of millions of years, this upper portion will get eroded and degraded and weathered and removed as well. Eroded and removed. So in those cases, when the top portion is eroded, weathered, and is then removed, what you have is, in that case, the magma chamber or the solidified portions, they get exposed. And that is how you have, or we get an idea of, that this might be an intrusive landform. So we get to see the intrusive landform only when the top portion is completely weathered, eroded, and removed, and then the bottom portion exposes itself. So you have a variety of intrusive igneous landforms. So when we talk about the variety, you have the presence of phacolith or the batholith. Then you have laccoliths. Then you have lopoliths. Then you have phacoliths. Then you have sills and sheets. And then you also have the presence of dikes. Now, all these various different landforms that you see, they are classified based upon the shape in which the solidification has happened, or based upon the shape that they have attained while cooling down, right? So one of the major classifying factors or the differentiating factor is the shape in which the solidification has taken place. So solidify in different shape. Okay. For example, when you have, let's say, the entire magma chamber in itself, when it solidifies, that ends up creating a dome-like feature that we refer to as batholith. When the molten materials, they spread out in very thin layers and then solidify, that is what we refer to as sheets. When they solidify in a kind of a vertical section like this, where they try to come out but they solidified, that is what we refer to as dikes, right? So that is how, depending upon how they have solidified, where they have solidified, you have the classification. So here, if you will observe, for example, take the case of this particular image where you will observe that this is the ancient or the old magma chamber, right? Now the molten material, they have tried to come out in various different sides, in various different directions. And as they have tried to emerge, as they have tried to come out, they have solidified in the process. In few areas, they might have come out, but otherwise they have solidified. And that shape in which they have solidified, that gives the name laccolith, dike, batholith, and so on. So when you have a batholith, so that is where the entire magma chamber in itself cools down and solidifies. That is what forms a batholith. So it is a large body of magmatic material that cools in the deeper depth of the crust molds in the form of very large domes. They appear on the surface only after the erosion and the weathering process or the denudation process eliminate the overlying materials, and the underlying materials, they expose themselves. This is an example of the dome-like feature indicated in a batholith, right? So you can imagine that at one point of time, there would have been significant amount of land mass on top of this. Okay, so over a period of time, lot of this land mass getting eroded, weathered, broken away, and also the elevation of the underlying layers, that is what has exposed this batholith for the current viewing. Now, then here we talk about laccolith. Now, laccolith is again a solidified portion of the magma itself, but here the solidification takes place where the molten material from the magma chamber tries to come up but is unable to break through the surface, but rather starts to solidify, right? Solidify in the form of a dome-like structure. So here you will find that the solidification happens in a kind of a dome-like structure. So that is again an intrusive landform. When the top portion is removed or eroded away, this is what the dome-like feature will appear to look like. That is what is referred to as laccolith. This is your example of laccolith. So at one point of time again, imagine that at one point of time in the past history, all of this would have been covered by thick deposits on top. And the top portions would have been eroded, weathered, disintegrated, and now these portions are exposed. So that is your laccolith. Then after that, we have the lopolith. Lopolith is a kind of a solidification where you have a flattish top. So in the case of a laccolith, what is the shape of the solidified material? Shape of the solidified material is having a flat base and a kind of a dome-like top. Okay, that is what a laccolith is. When we talk about lopolith, here it is the opposite, exact opposite. So here what you will have is a kind of a flat top and a shallow base that you have, which will be connected to a magma chamber or ancient magma chamber. So the shape of solidified material, if it happens like this, then it will be referred to as lopolith. So this can happen when the top crustal surface above it would be so very difficult to break through that maybe even there is no dome formation. So that is why the flat top. So this is the lopolith. Lopolith. Then after that, we have the phacolith. Here also solidification takes place, but solidification takes place within the layers of the rocks. Now the rocks in many of the cases, they have a kind of a compression. They experience a kind of a compression. So in general, if I take the example, let's suppose rocks will always, when they are getting compressed, they will indicate a feature which is varied somewhat like this. So if let's say in this type of feature or in this type of material, let's suppose the rocks are somewhat like this, compressed from both sides. So the rocks are getting arranged like this. So here, whenever you have such kind of a fold, so you will have an overlying portion or upward portion and a downward portion. This is what is referred to as an anticline. And this is what is referred to as a syncline. So many of the times, these molten materials, they will solidify here, gaining a kind of a saucer shape, or they will solidify maybe here within the layer of the rocks. So the solidified portion, they will indicate a shape somewhat maybe like this, or a shape somewhat like this. And that is what we gather as phacoliths. These are what are referred to as phacoliths. Okay. Then furthermore, after that, we talk about the sills and the sheets. So when we talk about sills and sheets, so many of the times the molten materials, they will rather spread themselves within the layers of the rocks in itself, how the layers of the rocks are, and how you have the various different types of layering in horizontal section. It will start spreading in between. So when they spread out in thick horizontal manner, That is what leads to the formation of a sill. So that thicker portion of solidified material that you observe, that will be referred to as a sill. And when they spread out in very thin films, that is what is referred to as sheets. Okay, so that is basically what you have as sills and sheet. Example, the image that you can see here, observe this particular image here. Observe this stretch. Now this represents a solidified horizontal portion, where at one point of time this would have lied under the land surface, significantly under the land surface, and at one point of time the molten materials would have spread there, solidified. So this is an example of sills. When they are very, very thin, that is what is referred to as a sheet. When they are thick, they are referred to as a sill. So in all these, please understand, the same process is happening. Solidification is happening inside the Earth's surface. But the shape that they gain while solidifying, that gives them different name and different classification. When we talk about dikes, dikes end up representing a vertical column of solidified magma. So wherever you have a vertical wall-like feature, like here, so it ends up representing a kind of a vertical section, where maybe an ancient vent or an older vent would have existed and it would have solidified. So the pattern in which the solidification is happening, that is associated with the name. So again, a very quick recap. When the entire magma chamber solidifies, batholith. When the magma tries to come out but forms a kind of a dome, then you have lacolith. Then when you have a kind of a solidification where the top is flat, the bottom is having a convex shape, that will be a lopolith. When the solidification will happen in between the foldings of the rocks, in the upward fold or downward fold, phacolith. When the solidification will happen in the horizontal section, a thicker solidification, sill. A thinner solidification, sheet. When the solidification will happen in the vertical section or a vertical wall-like column, that will be your dike. Okay. Now, then we come to the physical control of the eruption style or the chemical composition of the magma in itself. So magma, over a period of time, we have to understand that magma is having its own type of chemical composition. And the chemical composition that it has, the minerals that it has got, that ends up determining whether the eruption will be explosive, non-explosive, whether the magma will be fluidic or whether it will be viscous. Viscosity is what? Viscosity is ability to flow. So a highly viscous object will not be able to flow. So materials with low viscosity, they tend to flow easily. So broadly, the type of magma or the chemical composition of magma, that can be classified into two types. You have mafic and you have felsic. Mafic magma, that is the one which flows very easily. Observe here, it flows just like water. So it can spread over very large distances very quickly. Mafic here, Ma stands for magnesium. Fi here represents, Fic here represents iron. So this is rich in iron and magnesium. In iron and magnesium. Okay, that is something which is rich in iron and magnesium and is poor in terms of silica content. Poor in silica content. Now this lava which is created, that will flow easily. Flow easily. And when it flows easily, basically, it will always be accompanied by non-explosive eruption. Okay. Now, generally, the rocks which are created as a result of this, the mafic igneous rocks, they will be darker in coloration pattern. They will have a higher density. And also, they will, because they are rich in iron and magnesium, they will have some amount of magnetic property associated as well. So the rocks which are formed, or rocks formed from mafic, that will be having higher density, darker coloration, right? They will have darker coloration in them. Magnetic property will also be associated. Then you have ultramafic as well, where the percentage of silica is even further down, the percentage of iron and magnesium is even further up. And that is where, because they can flow easily, they won't have any air trapped in between them. That is why when they will solidify, they will have a very high density. But when we talk about felsic, here the viscosity is high, means it does not flow easily. And when you have that kind of a jelly like formation, or that kind of a globule like formation, it will have lot of air trapped, right? That is why it won't flow easily. Lot of air trapped in between. So when that will solidify, obviously the density will be much lower. So this is rich in silica, very rich in silica. Then poor in iron content, does not flow easily. Flow easily. Lot of air trapped in between. Trapped in between. Which basically means always you will have an explosive eruption. And the rocks which are created, rocks, the igneous rocks which are created, they will be lesser in density or lighter density, and will be lighter in coloration as well. Lighter coloration pattern as well. So that is the characteristic. Even if you have to classify, let's say, the igneous rocks, then you can classify based on the similar standard, that you have the felsic rocks, you have the mafic rocks. Now mafic rocks, now here you have to understand that it is their mineral composition which determines the flow pattern, which determines the behavioral pattern. So here magma types vary from mafic magma, which have very low silica and high iron and magnesium content, to felsic magma, which have higher silica and low iron and magnesium content. Now, viscosity of magma is an important factor, and silica content determines the viscosity. Silica content determines viscosity. Viscosity is the ability to flow. Now, in the case of felsic, what you have is that in those molten materials, lot of air is trapped. So let's suppose here you have a molten material. In that, you have lot of air bubbles in between. Lot of these air bubbles in between which are trapped. Now, obviously, it is not like a plastic that you can compress from both ends and the air will escape. The air has been trapped there. So for this to move, it will take a lot more amount of time, and when this will solidify, it will solidify with the air bubbles in between them, so the density will also be less, isn't it? So that is basically about the eruption style. So based on the silica content, here is a chart for your reference for your prelims purposes. So based on the silica content, you can see if the silica content is very low, that is the mafic magma, the viscosity is low, means it can flow easily. The gas trapped is also low, and it will be a non-explosive eruption. Then if the silica content is high, you will observe it is a felsic magma. Here the viscosity will be high, means it won't be able to flow easily. It has got a lot of gases which are trapped inside, and it will require an explosive eruption to come out. Intermediate, obviously, it will be the middle path of all of this. Now the extreme of this is ultramafic, right, where you have a greenish band or the greenish coloration of the rock develops. That is where you have the ultramafic included. Then we come to another important portion, and that is about the distribution of volcanoes, the global distribution of volcanoes. Now, globally, where is it that you will experience volcanic eruptions to occur? You will experience them to happen across the plate boundaries. Where? Which plate boundaries? The oceanic convergence and divergence in chief. That is where majorly you will find. Along with that, you will also find the volcanic eruptions to be happening across the region of volcanic hotspots. So here, you will find the eruptions to occur in the region of convergence, or better to write oceanic convergence, oceanic convergence, divergence of plates, and then also in the case of volcanic hotspots. Okay. So when we talk about oceanic convergence, here you can take the case of many areas of volcanic eruption. For example, you can observe that in the entirety of the region around the Pacific Ring of Fire, okay, in the entirety of the region where you have the Pacific Ring of Fire, you have volcanic eruptions which occur due to this. Tonga eruption, or be it the Pinatubo eruption in the region of Philippines, all of them are initiated due to convergence. Now, convergence also leads to eruption in this portion of Mediterranean. As we have discussed that the African plate is pushing into the region of Europe, significant portion of the Mediterranean Sea is undergoing compression. Portions are going or experiencing subduction. So that is where here also oceanic crust is involved. So here also you will experience an eruption. So the region of Mediterranean, where you have Etna, Vesuvius, Stromboli, all of these can be taken as an example. Then you can have divergence. So here you can take the case of Iceland, and in general, Mid-Atlantic Ridge. Mid-Atlantic Ridge. Then you have volcanic hotspots. You can observe volcanic hotspot in the region of Hawaii. And there is also another hotspot here in the Indian Ocean, that is the Reunion Island. So here Hawaii and Reunion Islands. Okay. So that is where you experience that distribution of volcanoes or existence of volcanoes. Now observe here the entire region around the Pacific Ring of Fire, this entire area wherever there is convergence happening. Okay, that is the Pacific Ring of Fire. In this area, why is it that there is some eruption in this area? Because of the region of the Nazca Plate and the East Pacific Rise, the East Chilean Pacific Rise or the Chilean Rise. Then here also there's convergence happening. Around this region, you have the oceanic plate here converging. Now, then Barren Islands is the northernmost volcanic eruption here. Now, then the eruption in this portion is because of the African Rift Valley. Eruption here is because of the mid Atlantic ridge, which is there. Eruption here is because of convergence again. So, if a question is asked in the examination that discuss about the global distribution of volcanic events or the global distribution of volcanoes, so you have to talk about that how the volcanic events are observed in various areas and what are the reasons for the same. You can take the examples also, provide a rough map of the world, and then you can justify your answer. Okay. Now, then we come over to the portion of folding and faulting. What do we mean by that? What is folding and faulting? So, till now, all the various events that we have studied, they have been initiated because of the forces which have been acting from the interior of the planet. That is why all of these have been initiated, isn't it? Because there is continuous existence of forces acting from the interior, the endogenic forces. Now, these endogenic forces, let's suppose this is the surface. Many of the times, these endogenic forces, in certain areas which are not the plate boundaries, they create a kind of a tensional movement, or a kind of a compressional movement, be it the plate boundaries or non plate boundaries. So, that tensional and compressional movement lead to the deformation of the crust, and that leads to creation of folds and faults. So, the tensional, so, due to endogenic forces, tensional and compressional forces act on the crust. That leads to folding. Folding means, if let's suppose this is the crust, this is getting folded. If you compress it from both sides, it can get folded. So that is what you regard as folding. Excuse me. Leads to folding and faulting. And what is faulting? When you have development of a crack, any kind of a large crack when it develops, that is faulting. So let us understand what are the various different types of folds and faults which are created. Folding basically is kind of a bend which is created in the earth structure, which is created in the rock in the response of the compressional force, which is compressing from both sides. Now, any fold that is created will have an upward rise, will also have a downward rise. Think about it. If let's suppose there is compression which is provided here, it will have an upward rise, it will also have a downward portion. So that upward rise, the upthrown portion, that is what is referred to as an anticline. That is known as the anticline. And the downward sunk portion, that is what is referred to as a syncline. Okay, that is what you have as anticline and syncline. Okay, so anticline is the upthrown portion or the upward portion of a fold. Syncline is the downward portion when you refer to any particular kind of a fold. Now, the types of folds that you have, that differs depending upon what is the amount of pressure being applied, the amount of force being applied from both sides, whether it is equal, unequal. Also, it depends upon for how long that force has been applied, whether the rocks are able to handle that stress or whether the rocks are breaking in the process. Because think about it, initially if I apply equal amount of force, how will the folding occur? In a very similar manner, in a very symmetrical manner. But if I keep on applying more force from one side, observe that the fold basically gets deformed. Further, if I apply the force, observe that the fold keeps on getting horizontal. Eventually, if I keep on applying, the rock will break from somewhere. So the classification of the folds that you will observe, that is primarily done based upon the nature that the folds take. the angle that the folds make. And it is largely determined by the application of forces, the amount of forces, the magnitude of forces being applied from both sides. For example, take the case of a symmetrical fold. Symmetrical fold is created when you have a symmetry in both the arms of that anticline. You have a symmetry. So observe here, while on top of the surface, on the ground surface, you will observe something which is very normal and natural and plain. But observe the folding that the rocks have encountered and have undergone. You will observe there is a kind of a similarity, isn't it? So this is created when you have equal amount of forces acting from both the sides. When you have equal magnitude of forces acting from both sides. So that is what ends up creating a kind of a symmetrical fold structure. Example, you can take the case of Andes. In the region of Andes, in certain regions of Shivaliks also, you will find symmetrical fold. So Andes, Shivaliks, for example, there also in certain areas, you will find the symmetrical fold. But over a period of time, as the force is being applied, it gets asymmetrical. The angle is not symmetrical anymore. The angle is not equal anymore. So that is where, over a period of time, when the forces, the magnitude of it gets distorted, or there is any kind of imbalance, then whenever there is a variation in the compressional stress from either side, you have an asymmetrical fold. So observe the asymmetrical fold on your screen. So here you will observe the nature of the fold. So it is somewhat like this, isn't it? It is not symmetrical anymore. On top of it, on the surface, you won't get an idea whether it is asymmetrical or symmetrical. But underneath that, all these rocks, observe here, they have a kind of an asymmetry here. So that is the asymmetrical fold. So in the ranges of Himalayas, you will find many of them. Even in the case of the Alps, you'll find many of them. In fact, in Himalayas, because the process of formation has been carried out for some time, the amount of pressure is also variable. So Himalayas are one of the ranges where you will find the evidence of all different kinds of folds to exist. So here, example can be Himalayan and the Alpine Cordillera in general. Okay. Now, this is your fold. Then you have the recumbent fold. Recumbent fold is also what is referred to as the sleeping fold or the horizontal fold. Because here the folding has happened so much, and from one side there is so much extent of the folding that the fold has almost become horizontal. That is why it is also referred to as a horizontal fold or a sleeping fold. So this is where the folding has become almost horizontal because of the forces applied. Now, this is your recumbent fold or what is also referred to as a sleeping fold. Now, let's assume here further there is significant amount of compressional force which is happening. What do you think will happen beyond this? Once it is already horizontal, what do you think the further amount of compression will lead to? Beautiful. Breakage. Breakage from where? Breakage from the point of contact, from the point of deformation here. It will break. And then what will happen? This portion will start getting shifted or pushed. So eventually, as the recumbent fold experiences the forces happening furthermore, then you will have the breakage of the fold, and that creates what is referred to as nappy or the broken fold. So here you will observe the nappy or the broken fold. This is created generally after the compressional force exceeds the deformative ability or the deformation ability of the rocks. So observe these folds here. You will observe these folds amongst the rocks. Here, observe there is a breakage in this particular portion. At one point of time, it would have been connected, but now it has broken. So once the force of compression exceeds the elastic limit of the rocks, that is when the rocks will break, and that is what creates a broken fold. So compressional stress surpasses the ductile characteristic of the rock. What is the meaning of ductile? Ductile basically represents the ability to be stretched into thin wire without breaking, thin wire like, or the ability to get stretched without breaking. That is ductility. Metals have that ductility, rocks don't have ductility. So when the compressional stress exceeds the elastic limit of the rocks, then rather than getting deformed, they get broken. And that is what you have as the nappy or the broken fault. Where will you find this example? You'll find this in Himalayas. Okay. In Himalayas, you have multiple different such broken folds where on top the mountain might appear to be like this, but underneath the rocks have underwent such huge amount of compression that a lot of these broken folds you will come across. Okay. Then we come to faulting. And here is the written text that all of you had been vying for, that give us the written text. We don't care of what is being told. So recumbent fold is also example. You can take the case of Himalayas. In fact, in many of the regions of Himalayas, you have evidences of the rocks being pushed for many kilometers from the point of breakage, which tells you the amount of compressional force. So here we come across the portion of faulting. What is a fault? Fault is nothing but a development of a large crack. Now, that large crack anywhere can come into existence because of compression, can also come into existence because of expansion. So, let's suppose this is a particular land surface. Now, if I start pulling it from both sides, that is the tensional force, what will happen? It will develop a crack, it will break. Or if this is a kind of a rock which cannot get folded easily, but I compress it. Suppose this is a kind of a rock. Now if I compress it, it will get folded. But take this case of a plastic pen. If I compress it, will it get folded? No, it will break. So that breakage which happens, it develops a kind of a crack, and that is what we refer to as a fault. So here, you just the development of a crack is not referred to as a fault. So you have different types. For example, so here a sudden stress on the rocks, they may reach the rupture point due to which the rocks can crack because of the tensional or compressional force. Due to tensional or compressional force. Okay. Now, in case if there's a breaking of a rock in any particular place, let's suppose in case there is a breaking of the rocks here, just like this, it won't be referred to as a fault unless and until there is a relative movement on both sides of the surface. It won't be referred to as a fault, it will be referred to as a joint. So if there is breaking of rock without a relative displacement on either sides of that crack, it is referred to as a joint. Then, if there is a development of a crack in such a way that one portion moves with respect to another, that is what is referred to as a fault. So when we talk about a fault, fault is the one where there is a crack which develops and there is a respective movement associated on both sides of that crack. So that is basically a fault. So let's suppose you have a rock like this, a large crustal portion like this. Let's suppose there has been a development of a crack throughout and there's a movement. Now, after some time, you will observe here, it will lead to a kind of a structure somewhat like this, where there has been some amount of movement. So the movement which is happening here across this entire plane like structure, that is what will be referred to as the fault plane. This will be referred to as the fault plane. Okay, that is how faulting occurs. Now, faulting can occur both due to tensional and compressional stress. Now, where is it that, let me ask this question, where is it that this compressional and tensional stresses are born from? Why is it that we have the compressional or the tensional stresses that we experience? All the compressional and tensional stresses that we have been talking about. Why is it that we have the compressional and the tensional forces? Convection current, very good. Endogenic forces, perfect. Perfect. Very good. So, because of endogenic forces, correct. So, because of the internal forces or the forces acting from interior, that is the endogenic forces, that is why you have the creation of this tensional or compressional stress. And that is why you have these kind of folding and faulting events which are created. Okay. Now, let us take a look at the type of faults. Now here, one of the type of the fault that you will observe, the normal fault that is experienced. This is something that you would have experienced on in many of the instances as well, where you would have observed that the land is flat and suddenly the land is having some amount of elevation, and then again a kind of a flatter portion of or a series of small hillocks, or so to say. That is a normal fault. Normal fault is basically created due to tensional stress, right? So let's assume you have the crustal portion. Let's assume you have the crustal portion. Now there is significant amount of tensional force happening, acting here. Now as the tensional forces are acting, initially it will get pulled slowly and steadily. See, if this is the pen, if I'm pulling it from both ends, even though I don't have enough power, but if I had, let's suppose, had got enough power and I would have managed to pull it here, it would have developed a crack in between, isn't it? It would develop a crack somewhere here, maybe a crack here also. Eventually this crack will meet. Now then, furthermore, if I pull it up, what will happen? One portion will simply slide underneath, and you will have a creation of a landmass somewhat like this, where if you observe this, that landmass overall, let's assume somewhat like this, a portion of the landmass would have simply subsided or subducted, right? And this is the landmass that you will observe. Now you would observe that it is here that the sliding has taken place. This is what is referred to as the fault plane that we were talking about. Fault plane. Over a period of time, this will get eroded because it is a sharp edge. Nature doesn't like sharp edges ever. Keep that in mind. Out in the nature is never appreciative of a sharp edge. Wherever a sharpness is created means over a period of time, nature will blunt it out. It will get eroded, it will get smoothened. Right. So if there is a sharp edge, it will get rounded over a period of time due to erosion, weathering events, etc. So after a period of time, you will observe the creation of a landform somewhat maybe like this. Now, this is an uprised portion where over a period of time due to erosion, maybe you will have certain peak-like features which will develop. But these peak-like features, can we consider them as mountains? No, these have been created due to fault. So these are what are referred to as escarpments. escarpments. Example, yes, faults will lead to earthquake because there is a relative movement of the rocks. It can always initiate earthquake. Example of escarpment, you have Western Ghats. Very good, Garvit. So Western Ghats is an example of escarpment. We'll study in the portion of Indian geography that how Western Ghats are an escarpment, how there has been a creation of a fault there. So escarpments basically are the remnant portion. One portion of it subsides, sinks down, other portion remains like a kind of a mountainous feature. That is what is referred to as an escarpment. Then you have a reverse fault. What is a reverse fault? Here, the fault is created due to compressional force, not because of tensional force. So here, it is produced from the compressional force. So where, think about it, if let's suppose the two hands, the two palms of my hand, they represent, let's say, a joint land portion, a combined land portion. If there's a compressional force, and let's suppose the land cannot get folded, what will happen? Beyond a point, it will crack, and then one will ride over the other, one will simply climb over the other, isn't it? Similarly, think about it as this pen. If I compress it from both sides significantly, if I put all my force here, it will break. One portion will climb over the other. That is a reverse fault. So here, basically, assume that again, if this is the rocky portion, and there's significant amount of compression. Okay. So when this is having a significant amount of compression, if it cannot get folded, it will develop some kind of a crack-like pattern, maybe. And that crack eventually will form a kind of a fault. Now, furthermore, if the compression continues, what will happen? This portion will try to ride over the other. So you have a portion which has ridden over the other. You have a slight upward movement. So here, because one portion rides over the other, whereby it is in a way defying gravity, because as per gravity, everything should come down. So one portion is riding over the other because of the compressional force. That is why it is a reverse fault. Okay. So it is in reverse of the sense of the gravity. Why? Because the one portion upper block slides up the incline of the fault plane. So one portion of the block simply rises up. So that is where in an existing landmass, a crack will develop and it will simply ride over the other. That is what creates a reverse fault. Then you also have a combination of these faults. When you have a combination of two normal faults, that is what many of the times creates a graben, or what is also referred to as a rift valley. Rift valley we had earlier seen in the case of plate movement as well. But this is not associated with a kind of a plate or a plate boundary. This can happen anywhere. So here, when you have combination of two normal faults, combination of two normal faults. Now, how does the process happen, or what is the process in total? So let's suppose we have this as the larger rock. Now there's a tensional force. Now it might develop a crack here. It might end up developing a crack here also. Over a period of time, over the period of hundreds and thousands of years, this, due to the tensional force, the crack will further deepen. Right? Now, after that, again, as there is a tensional force, what will happen? Imagine this. What will happen in this case? The central portion simply will subside. As the other portions are drawn apart, the central portion will simply subside. It will sink. Perfect. So here, what do you have? You have a creation of a kind of a depression, a valley-like structure. So that is what you refer to as a rift valley. Why rift? Rift represents a kind of a tensional force. So here you have the formation of rift valley. So rift valley or a graben fault is a combination of two normal faults. Example, you have Narmada Rift Valley. Then you have Damodar Rift Valley. Okay, these are your examples of graben. Now, here we saw the combination of two normal faults. Similarly, we can also experience the combination of two reverse faults in the sense that let's say there is compression in a larger area. Let's suppose there is compression. Okay, let's suppose there is a compression. Now, here, as the compressive forces act, there can be development of crack here also. Let's suppose there's a crack developing here, there's a crack developing here also. As the compressional forces continue, the cracks will further deepen, right? They will create a kind of a fault. Now, after that, if you continue to compress, what will happen to the central portion? If you continue to compress, what do you think will happen to the central portion? The central portion will be thrown upwards, isn't it? It will be thrown upwards. So you will observe the formation of a structure somewhat like this. A structure somewhat like this. Now here, oftentimes that is what is referred to as the Horst fault. And this kind of a upraised portion, it does not resemble a fold mountain. But over a period of time, due to erosion, here also you will observe development of peak-like features. So this is what is also referred to as a Horst fault or a block mountain. Example, very good. You have Vindhyas, Vosges. Yes, sometimes it can end up creating a kind of a plateau-like structure, but mostly it will create a block mountain. Vosges in Europe, Vindhyas and Satpura, I hope we are aware where it is. So that is the Horst fault. In general, how does it exist naturally is that wherever you have the creation of, let's say, parallel and simultaneous Horst, in between them, you will have a kind of a graben-like feature. So in reality, if you take a look at it, so let's suppose this is what represents the Narmada Rift Valley system, right? So here you will have on one side the Horst getting eroded from different sides, creating peak-like feature. So you have Vindhyas. On the other side, you have Satpura. And then you have Narmada Rift Valley. Rift Valley. Okay. So that is about folding and faulting, which is all initiated due to the endogenic forces. Endogenic forces. This is independent of your plate movement. This is a force acting on the surface because of the convection current, which is initiated by the endogenic forces. Okay. Now, let us end the session or limit the discussion here itself, and let us take certain questions, and then we will end the session. Abhiraj, please change this violate. Correct the spelling of violate first of all. Background because the printout is not come. So I think you have a section where the PPT is available with white background as well. Take a look into that and ask on IS Live. Uh, Graben fault is basically Lakshmi is created when you have a significant amount of tensional force where the central portion simply sinks because of development of two escarpments or two normal faults. That is a Graben. Yes, Tehsin, this is where we'll limit the discussion for today. Denudation process, Madhuri, refers to the process of erosion, weathering, where the top surface is eroded and removed. That is denudation. We can say that mafic magma comes directly from outer core and felsic magma come from asthenosphere. Absolutely not, Anubhav. Absolutely not. Please understand that in very rare cases, we are able to decipher that yes, this magmatic material has come from the region of outer core. But majority of the magmatic material that is erupted, that is pushed up, that comes from the region of the asthenosphere itself. Only in the hotspots, you also have the condition where it is provided from the region of outer core, around the region of Gutenberg discontinuity. Okay. And then please bring the slide of host fault. Okay, Anurag. And mapping Gulam will give tomorrow. What is the difference between laccolith and bacolith? First of all, there is nothing as bacolith, there is a batholith. So when we talk about batholith, the entire magma chamber in itself has cooled down. When we talk about laccolith, the magma chamber has actually observed the rise of magma, but then that magma, after rising, it has cooled down somewhere above in a dome-like formation. So it is not the entire magma chamber which has cooled down. So that is the difference. In Rift Valley, why does the subduction doesn't happen? Subduction does happen, Sayyid. Observe here, the subduction does happen, isn't it? This undergoes subduction. Faulting, Shiva, refers to the development of a crack. That is what is faulting. Reverse fault basically happen in a flat place. Yes, Lakshmi, that is correct. Giant distribution of volcanoes slide. Okay. So this is the distribution of volcanoes. Is convergence and faults the same? No. Convergence is when you have two plates moving towards each other. Faults can develop in between the plates as well. So, for example, if let's suppose you have a larger plate which is meeting with another plate, so convergence is happening here. But within the plate here, you can have development of a fault due to maybe compressional force here, due to maybe tensional force here. So, fault can happen anywhere. Most of the magma is in outer core or is in asthenosphere. In terms of when we talk about the presence of the molten or the volcanic eruption, the lava, molten lava, that is supplied majorly from asthenosphere itself. Nitin, I hope you are getting. Yes, I see your text, Nitin. Endogenic forces and convection current are the same? Chetan, no. Endogenic forces are all the various forces acting from the interior. One of those forces that ends up getting created, one of those events that ends up getting created due to the residual heat is convection current. Okay, and Vani, because okay, today's session, you thought about any portion that you have not understood. Vani, let me know about that, because many of these theoretical portions which are written as text in the slide, I don't want you to indulge in a kind of a very basic simplistic class 9th and 10th level of classes where I will read up what is written in the slide and you will also read up along with me like you did in your school days. Any doubts that you have faced in the conceptual understanding, that is something which is to be pointed out. Please understand, in these portions, if we don't elevate the level of discussion, you will always be sticking to the portion of the NCRT itself. The level of discussion that any particular class has, that a class goes through, a class of student here, now that is very much dependent on the students themselves. See, I can hold the discussion up till this level, I can elevate the discussion up till here as well. The reason why I pulled faster in the portion of the text is so that this is something which is given in the text, it is easier to understand. Again, tomorrow when we will be talking about the landforms, that is easier to understand. I want you to stress more time in building concepts. Text, reading that, This session is not a replacement for books. If you have a kind of a preconceived notion that if we are sitting in the class, that is my book reading, that is how each and every sentence will be read, and I will be able to clear the exam, let me burst the bubble here itself. It is not going to help you clear the exam unless and until you read it, revise it on your own. No class will help you clear the exam. Bring the chairman of the UPSC also. So this is to show you the idea about how to gain conceptual clarity. If there's a conceptual issue, please feel free to raise it at any point of time. Okay. And Divya, shield and dome volcanoes appears to be the same. So it is same itself. Dome is the landform created. Shield volcano is the name of the volcano. Caldera, Sandeep, basically means that whenever you have a volcanic eruption, in certain cases, in the last phase of volcanic eruption, the central portion simply subducts, creating a large hole in between or a subducted portion in between. That is a caldera. Okay. And will faults can cause earthquakes? Yes, Mayank, they can. Bhagya transform fault are the plane of separation generally perpendicular to the mid-oceanic ridge. Yes, that is correct. Because here, please understand, when you have a mid-oceanic ridge, for example, let's suppose here there is a divergence which is happening. Now, this is your mid-oceanic ridge. Now, the entire plate on one side won't be moving at the same speed. So here, if there is a divergence, that will create a kind of a fault as the plates are moving parallel to each other with different speed. So look at it. This is perpendicular to the point of divergence, isn't it? Aravali was created due to folding, one of the oldest fold mountains that are present. That is how Aravalis are created. Lacolith and batholith is something that I have already explained. Look at the about this question also I have explained, Garvit, already. Endogenic forces are limited to crust and asthenosphere. Even below that, that is initiated even below that. Uh, Shanmugapriya, a normal fault is created when you have a tensional force due to which there is development of a kind of a crack and one portion simply undergoes subduction, creating a kind of a scarp plane. That is what we refer to as a normal fault. Okay. Ananya, yes, Horst and Graben fault, we have already shown you the example. Rashida, what is your question, my dear friend? I'm only be able to look that. Please take my question, but I'm not able to look at your doubt. Are the island nations like Indonesia, Philippines, and Malaysia volcanic landform? Indonesia, Philippines, Kumari, and all those archipelagos, islands that you find, they are of volcanic origin. Why? Because of oceanic convergence. Yes, Yuvraj, you can start reading NCRTs. Yes, Abhishek, that is correct. Uh, Gadamidi, is tablet recorded videos and live lectures same content? Yes, more or less. In the live lectures, you have more portion about the current aspect, but in tablet, you have many portions which we have discussed in detail otherwise also. Yes. And if there is any mantle plume, VK Kush, then will it always alive or it will be silent after some time? So it can exist for certain few millions of years in one part, a few hundred millions of years, and then it might subside or might erupt from some other location. Okay. And what are the other endogenic forces other than the convection current? Chetan will take a look at it tomorrow. Sometimes what happens is that you have the land simply rising up, the land getting uplifted or the land sinking down. That is also initiated due to the endogenic forces.